think of black holes as the universe's dead ends, collapsing stars, crushing gravity, and points of no return. But what if they are also beginnings? Tonight we drift into a question that turns destruction into creation. What if black holes are seeds for new universes? When we gaze at the night sky, we see only what light allows us to see. Stars burning brightly, planets reflecting their glow, and galaxies spiraling in the darkness. But scattered throughout our cosmos are places where light itself surrenders, where the familiar rules of our universe seem to end. These cosmic voids, these black holes, have captivated our imagination since their theoretical discovery. They appear as absence, as emptiness, as endings. A star that has burned through its fuel collapses under its own weight, crushing down to a point so dense that nothing, not even light, can escape its gravitational pull. It creates a boundary in space, a horizon beyond which we cannot see. It seems like the final page of a cosmic story. Yet in the quiet corners of theoretical physics, a beautiful idea has taken root. What if these apparent endings are actually doorways? What if each black hole in our universe is creating something new, something we can never directly observe? What if through some cosmic alchemy, these points of ultimate destruction are also points of ultimate creation? As you rest and listen, we invite you to journey with us to the edge of known physics, to the boundary between what we understand and what we can only imagine. We will explore how the death of stars might birth entirely new realities, how the darkness at the center of a black hole might harbor the light of a new beginning. The universe whispers its secrets in the language of mathematics and observation, and one of its most profound whispers suggests that creation and destruction are not opposites, but partners in an eternal dance, that the end of one story might be the first word of another. So close your eyes and let your mind drift toward the event horizon, that boundary between what we know and what we can only dream. Beyond it may lie not just the crushed remains of stars, but the glowing embers of new cosmos, new laws of physics, new possibilities unfolding in dimensions we cannot access. The night sky above you holds countless black holes, and perhaps, just perhaps, each one cradles a universe within. A universe that might one day look up at its own night sky and wonder about its origins, never knowing it was born in the darkness of another reality's collapsed star. This is not just a story about endings. It is a story about beginnings that emerge from endings, about creation hidden within destruction, about the possibility that nothing truly ends, but only transforms into something new, something unexpected, something beautiful. Drift now into the gentle gravity of this cosmic question. What if black holes are not the universe's dead ends, but its nurseries? What if they are not where things disappear, but where new universes appear? What if the darkness we perceive hides the birth of countless new lights? Imagine for a moment the birth of a star, a swirling cloud of gas and dust collapsing under gravity, growing hotter and denser until nuclear fusion ignites in its core, bringing new light to the cosmos. Now imagine its death, millions or billions of years later, when that same star, having exhausted its nuclear fuel, collapses inward, sometimes forming a black hole. We see this as an ending, a final chapter. But perhaps it is merely a transformation, like a caterpillar entering a chrysalis. The physics of black holes pushes our understanding to its limits. At their centers, our equations break down. Space and time as we know them cease to have meaning. This mathematical breakdown has long been seen as a problem to solve. But what if it's not a flaw in our understanding, but a feature of reality itself? What if this breakdown signals not an end to physics, but a transition to a different kind of physics, a different kind of existence? Throughout human history, we have reimagined our place in the cosmos. Once we thought Earth was the center of everything. Then we learned we orbit the sun. Then that our sun is one among billions in the Milky Way. Then that our galaxy is one among billions in the observable universe. Each revelation expanded our conception of reality. The idea that black holes create new universes would be another such expansion, suggesting that our entire universe might be just one bloom in a vast garden of realities, each sprouting from the collapsed core of a star in another universe. The concept challenges our very notion of what everything means. If each black hole gives birth to a new universe, then reality is not a single timeline or a single space, but an ever-branching, ever-growing tree of existence. Each branch giving rise to new branches, each universe seeding new universes in an eternal process of cosmic reproduction. As we follow this idea through the night, we will explore how it reshapes our understanding of space, time, creation, and perhaps even purpose. We will consider how the life cycle of stars could be part of a larger life cycle of universes, how the constants of nature might be passed down like genetic traits from parent universes to their offspring, how the apparent fine-tuning of our universe for the emergence of complexity and life might be explained by this cosmic evolution. The darkness of a black hole might not be empty at all, but pregnant with potential, holding within it all the energy and information needed to birth a new reality. Just as a seed contains all the instructions necessary to grow into a tree, a black hole might contain everything needed to blossom into a cosmos. Think of it this way. When we look at a black hole, we see only an absence, a place where stars and light vanish. But if we could somehow see from the other side, from within the new universe it creates, we might perceive it as a brilliant explosion of energy, as the beginning of everything, as a Big Bang. Perhaps our own universe emerged from such a process. Perhaps the Big Bang that birthed our reality was actually the other side of a black hole in another, older universe. If so, we carry within us the legacy of that parent cosmos, its physics echoed in our own, its matter transformed into the stuff of our stars, our planets, our bodies. As you drift towards sleep, consider this dance of destruction and creation, playing out across realities we cannot see. Consider that the seemingly empty darkness between stars might be filled with unseen connections to other worlds, other possibilities. Consider that what we perceive as the most destructive force in our universe might actually be the most creative force in the larger tapestry of existence. The coming hours will take us deeper into this possibility, examining the physics, the mathematics, and the philosophical implications of universes born from black holes. We will journey to the center of collapsed stars and beyond, to the theoretical landscapes where our universe might be just one among many, all connected through the hidden doorways we call black holes. Rest now as we begin this cosmic journey together, floating through the stars toward the darkness that might be the womb of worlds. Before we journey to the edge of understanding, let us first ground ourselves in what we know about these cosmic enigmas. Black holes are regions of space-time where gravity is so intense that nothing, not even light itself, can escape once it passes a boundary called the event horizon. Imagine standing on Earth. When you throw a ball upward, gravity pulls it back down. If you throw it harder, it goes higher before returning. But if you could throw it fast enough, about 11 kilometers per second, it would escape Earth's gravity entirely. This is our planet's escape velocity. For a black hole, the escape velocity exceeds the speed of light itself, and since nothing can travel faster than light, nothing can escape. Black holes begin their lives as stars, cosmic furnaces fusing hydrogen into helium, releasing the energy that makes them shine. A star exists in a delicate balance between two opposing forces. Gravity pulls inward, trying to collapse the star, while the energy from nuclear fusion pushes outward. For billions of years, these forces remain in equilibrium, and the star burns steadily. But stars do not burn forever. Eventually, a massive star consumes its nuclear fuel. When this happens, the outward pressure that counteracted gravity diminishes. Gravity, ever patient, begins to win the cosmic tug of war. The star's core collapses. For stars like our Sun, this collapse stops at a certain point, creating a white dwarf, a dense remnant about the size of Earth. But for stars with masses at least 8 times that of our Sun, the collapse continues. If the star's mass is between 8 and 20 times our Sun, it might become a neutron star, where protons and electrons are crushed together, forming neutrons. These neutron stars are incredibly dense, packing the mass of our Sun into a sphere just 20 kilometers across. But for the most massive stars, those more than 20 times the mass of our Sun, even the pressure of neutrons cannot halt the collapse. Gravity crushes the star beyond our current understanding of physics. The star's matter is compressed to a mathematical point of zero volume and infinite density, what physicists call a singularity. Around this singularity forms the event horizon, the point of no return. Black holes come in different sizes. Stellar black holes, born from collapsed stars, typically have masses between 5 and several tens of solar masses. Supermassive black holes, found at the centers of most galaxies, including our own Milky Way, can have masses millions or billions of times that of our Sun. How these giants formed remains one of astronomy's great mysteries. Then there are the theoretical primordial black holes, which might have formed in the extreme conditions of the early universe, potentially as small as a grain of sand but containing the mass of a mountain. The space around a black hole tells a story of extreme distortion. Einstein's general relativity describes gravity not as a force but as a curvature of spacetime. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. A black hole curves spacetime so severely that paths through space and time bend back on themselves. If you were to approach a black hole, you would experience time dilation, one of the strangest effects of Einstein's relativity. Time would pass more slowly for you than for observers far from the black hole. If you could hover just outside the event horizon, each second of your time might correspond to minutes, hours, or even years for someone watching from Earth. As you cross the event horizon, the outside universe would seem to accelerate, the distant future unfolding before your eyes like a cosmic fast-forward. Stars would be born, live their lives, and die in what would seem like moments to you. But you would notice nothing special about crossing this boundary. No alarms would sound, no walls would appear. The event horizon is not a physical surface but a point of no return, a one-way door in the fabric of spacetime. Once inside, all paths lead to the singularity at the center. Every direction you might choose to travel would lead you closer to it. In our understanding of classical physics, nothing can prevent your journey to the singularity. But it is here, at the center of a black hole, where our understanding breaks down. The laws of physics as we know them cannot describe what happens at a singularity, where density becomes infinite and volume becomes zero. Black holes also store information in a unique way. The entropy, or measure of disorder, of a black hole is proportional not to its volume, but to the surface area of its event horizon. This strange property has led physicists to propose the holographic principle, suggesting that all the information about what falls into a black hole is somehow encoded on its boundary. For decades, physicists thought black holes were completely black, that nothing could escape them. But in the 1970s, Stephen Hawking showed that quantum effects near the event horizon cause black holes to emit radiation and slowly lose mass. This Hawking radiation means that given enough time, black holes will evaporate completely. A stellar mass black hole might take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. When we observe the cosmos with our telescopes, we cannot see black holes directly. They emit no light. Instead, we detect them by their gravitational influence on nearby stars and gas, or by the radiation emitted when matter falls into them. As gas spirals into a black hole, it heats up to millions of degrees, emitting X-rays before crossing the event horizon. In 2019, the Event Horizon Telescope collaboration captured the first direct image of a black hole's shadow against the glowing gas surrounding it. A supermassive black hole at the center of Galaxy M87. This historic image confirmed a century of theoretical work and opened a new era in the study of these cosmic enigmas. The journey of our understanding of black holes spans over a century, beginning with Einstein's general relativity in 1915. From this theory, Carl Schwarzschild derived a solution that described the spacetime around a perfectly spherical mass. This solution contained a peculiar feature, a radius at which time and space would behave strangely. For decades, physicists debated whether this Schwarzschild radius was merely a mathematical artifact or a physical reality. It was John Wheeler who coined the term black hole in 1967, giving a name to these cosmic prisons. The name captured the public imagination, conjuring images of cosmic whirlpools devouring everything in their path. But the reality of black holes is both more subtle and more profound than this popular conception. Black holes are not cosmic vacuum cleaners, indiscriminately pulling in all matter around them. Their gravitational pull follows the same inverse square law as any other massive object. If our Sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. What makes black holes unique is not their gravitational strength at a distance, but the fact that their mass is concentrated within their event horizon, creating a region from which nothing can escape. The formation of a stellar black hole is one of nature's most dramatic events. As a massive star exhausts its nuclear fuel, its core begins to collapse. The outer layers fall inward, rebounding off the dense core in a spectacular supernova explosion that can briefly outshine an entire galaxy. While the outer layers are blasted into space, enriching the cosmos with heavy elements forged in the star's interior, the core continues its relentless collapse, crossing the threshold to become a black hole. Supermassive black holes tell a different story. Those giants, with masses millions or billions of times that of our Sun, likely formed through a combination of processes. They may have begun as smaller black holes that merged over time, or perhaps they formed directly from the collapse of enormous clouds of gas in the early universe. Their growth continued as they consumed surrounding matter and merged with other black holes. Almost every large galaxy harbors one of these giants at its center, including our own Milky Way, whose central black hole, Sagittarius A star, has a mass equivalent to about 4 million suns. The environment around a black hole is among the most extreme in the universe. As matter falls toward a black hole, it typically forms an accretion disk, a flattened ring of gas and dust swirling around the event horizon, like water circling a drain. Friction within this disk heats the matter to millions of degrees, causing it to emit energy across the electromagnetic spectrum, from radio waves to X-rays. These emissions allow astronomers to detect and study black holes indirectly. Jets of energetic particles often erupt from the regions near a black hole's poles, accelerated by complex magnetic field interactions to speeds approaching that of light. These jets can extend for thousands of light years, influencing the evolution of entire galaxies. In this way, black holes, despite their relatively small size, can shape cosmic structures on the grandest scales. The precise nature of a black hole's interior remains one of the great unsolved mysteries in physics. Einstein's general relativity describes how space-time curves around a black hole, but it breaks down at the singularity, predicting infinite values that cannot represent physical reality. It's at this boundary of our understanding that new physics must emerge, perhaps from a quantum theory of gravity that reconciles Einstein's description of gravity with the quantum world of subatomic particles. Some theoretical models suggest that inside a black hole, space and time might swap roles. Outside the event horizon, we can move freely in space, but are inexorably carried forward in time. Inside, we might be free to move in time, but would be inexorably drawn toward the center in space. Such a reversal challenges our intuition, but emerges naturally from the mathematics of general relativity. The temperature of a black hole, as described by Hawking radiation, is inversely proportional to its mass. A stellar mass black hole would have a temperature of less than 1/1,000,000th of a degree above absolute zero, making it colder than the cosmic microwave background that fills our universe. In contrast, a microscopic black hole with the mass of a mountain would blaze at billions of degrees, evaporating in a flash of energy. This connection between black holes and thermodynamics, established by the work of Hawking, Jacob Bekenstein, and others, revealed deep insights into the nature of information and entropy. A black hole's entropy, proportional to its surface area, represents the amount of information it contains. This led to the holographic principle, one of the most profound insights of modern physics, suggesting that the information describing a volume of space might be encoded on its boundary. Some physicists speculate this principle might apply to our entire universe. The discovery that black holes can merge has opened new windows into the cosmos. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves from two black holes spiraling together and merging. This landmark observation confirmed another prediction of Einstein's general relativity and inaugurated the era of gravitational wave astronomy, allowing us to hear the universe in an entirely new way. As we continue to study these cosmic enigmas, new questions and possibilities emerge. Could microscopic black holes be created in particle accelerators, offering glimpses into extra dimensions of space? Might the information that falls into a black hole re-emerge in another form, preserving the quantum coherence of the universe? Could black holes be bridges to other regions of space-time, or even to other universes? They pull in light, time, and space itself, consuming stars and reshaping galaxies. They represent the ultimate end, where our understanding of physics reaches its limits, but perhaps not forever. Because at the edge of our knowledge, where mathematics breaks down and intuition falters, a new possibility emerges. Perhaps these cosmic endings are also beginnings. Perhaps what appears to be destruction from our perspective is creation from another. Perhaps beyond the event horizon lies not just the end of everything that falls in, but the start of something entirely new. Now we venture beyond the event horizon into realms where even our most sophisticated theories begin to fray. What happens at the very center of a black hole? This question has puzzled physicists for decades and continues to inspire new theories about the nature of space, time, and reality itself. According to Einstein's general relativity, the matter of a collapsed star continues to fall inward until it reaches a point of zero volume and infinite density, the singularity. Here, the curvature of space-time becomes infinite. The mathematics breaks down, offering us no clear picture of what actually happens. It's as if nature is telling us that our current understanding is incomplete. Imagine approaching this central region. As you fall deeper into the black hole, the difference in gravitational pull between your head and your feet would stretch you vertically and compress you horizontally, an effect physicists call spaghettification. For stellar mass black holes, this tidal force would tear you apart long before you reached the singularity. For supermassive black holes, with their gentler gravitational gradients, you might survive past the event horizon, but the singularity would still be your ultimate destination. Inside the event horizon, space-time warps so severely that the direction toward the singularity becomes time-like rather than space-like. What does this mean? Outside a black hole, you can choose to move in any spatial direction, but you always move forward in time. Inside the event horizon, this changes. You can no longer choose whether to move toward the singularity, just as you cannot choose whether to move forward in time under normal circumstances. The singularity lies in your future, not merely in a spatial location. This is why nothing can escape a black hole after crossing the event horizon. To escape would require moving backward in time, which is impossible according to our current understanding of physics. But the notion of a singularity, a point of infinite density, troubles physicists deeply. Infinities in physical theories often signal that something is missing in our understanding. We faced similar infinities in quantum electrodynamics before the development of renormalization techniques, which revealed that these apparent infinities were artifacts of our mathematical approach rather than physical reality. Many physicists believe that a complete theory of quantum gravity will remove the singularity from black holes, just as quantum mechanics removed the singularity from the electron orbits in the hydrogen atom. But we don't yet have such a complete theory. Several approaches to quantum gravity offer different perspectives on what might lie at a black hole's center. String theory suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings. In this framework, there might be a minimum possible size for objects, preventing infinite compression and thus avoiding a true singularity. Loop quantum gravity, another approach to quantum gravity, suggests that spacetime itself has a granular structure at the smallest scales, like pixels in a digital image. This quantum foam would prevent the formation of a singularity by limiting how tightly space can be curved. Some theoretical physicists propose that the center of a black hole might contain a region of space where the laws of physics are fundamentally different, a pocket universe with its own rules. Others suggest that matter falling into a black hole might be converted into pure information encoded on the event horizon, never actually reaching a central point. The physicist Lee Smolin has proposed that the interior of a black hole might undergo a process similar to cosmic inflation, rapidly expanding to form a new universe disconnected from our own. In this view, the singularity becomes a bridge rather than an endpoint. Another intriguing possibility comes from the work of physicists exploring the connection between black holes and wormholes, theoretical tunnels through space-time. Perhaps the interior of a black hole connects to a white hole, a theoretical time-reverse black hole that only emits matter and energy rather than absorbing them. This white hole might exist in another region of our universe, or perhaps in another universe entirely. Roger Penrose, who won the Nobel Prize in Physics for his work on black holes, proposed the concept of cosmic censorship, suggesting that singularities are always hidden behind event horizons, preventing their influence from reaching the outside universe. This would mean that the laws of physics break down only in regions that are causally disconnected from the rest of the universe. But what if the singularity isn't truly a singularity? What if it's a phase transition, like water turning to ice, but for space-time itself? Perhaps matter reaching this point doesn't encounter infinite density, but transforms into something else entirely, something beyond our current physical models. The question of what happens at the center of a black hole intertwines with other profound puzzles in physics. The black hole information paradox asks what happens to the information contained in matter that falls into a black hole. Quantum mechanics suggests that information cannot be destroyed, yet black holes seem to destroy it. Stephen Hawking later proposed that the information might be preserved in subtle correlations in the Hawking radiation, emitted as black holes evaporate, but the debate continues. As matter falls into a black hole, it carries with it all the complexity and structure it possessed, all its physical and quantum properties. Where does this information go? Does it somehow remain encoded on the event horizon? Does it transfer to another region of space-time? Or does it truly vanish, challenging one of the fundamental principles of quantum physics? Some theorists propose that when enough matter falls into a black hole, the central region might reach a critical point where traditional space-time concepts break down entirely. Instead of a singularity, there might be a transition to a state where space and time cease to be fundamental and emerge from deeper physical principles. The holographic principle, inspired by black hole thermodynamics, suggests that all the information about the three-dimensional interior of a black hole might be encoded on its two-dimensional surface. This principle has profound implications for our understanding of space itself, suggesting that what we perceive as three-dimensional reality might emerge from information encoded on a distant boundary. The journey to the center of a black hole takes us through regions of ever-increasing strangeness. Just after crossing the event horizon, the outside universe would still be visible, though distorted and blue-shifted. Light from the external universe would still reach you, concentrated in a small, bright circle directly above. As you fell deeper, this window to the outside would shrink and brighten until it becomes a brilliant point and then vanishes altogether. Beyond this point, you would be truly isolated from the universe you left behind. Your future would lie entirely within the black hole. The remaining journey would be brief by your reckoning, perhaps just seconds or minutes depending on the black hole's mass. But during this time, you would witness some of the most extreme conditions imaginable. The curvature of space-time would increase dramatically as you approach the center. In a rotating black hole, this might create a ring-shaped singularity rather than a point. This ring, known as a Kerr singularity, after the physicist who first described it mathematically, offers more complex possibilities than a simple point singularity. Some calculations suggest you might even pass through this ring without encountering infinite density, emerging in a different region of space-time entirely. But these are still classical descriptions, relying on general relativity alone. Most physicists believe that quantum effects would become increasingly important as you approach the central region, fundamentally altering the nature of space and time in ways our current theories cannot fully describe. One possibility is that space itself becomes discrete rather than continuous at these scales. Just as matter, which appears smooth and continuous to our everyday perception, is actually composed of discrete atoms and subatomic particles, space-time might have a fundamental atomic structure at the smallest scales. This quantum granularity might prevent the formation of a true mathematical singularity, replacing it with an extremely dense but finite state. Another possibility comes from string theory, where the fundamental constituents of reality are not point particles but tiny vibrating strings. In this framework, there's a minimum possible size for objects, preventing the infinite compression that would create a singularity. Instead, as matter falls into a black hole and approaches maximum compression, it might undergo a phase transition to a state of string soup, a jumble of highly energetic strings that could seed the formation of a new space-time region. Some physicists have suggested that the interior of a black hole might be describable as a Bose-Einstein condensate, a state of matter in which quantum effects become apparent at macroscopic scales. In this view, the collapsing matter would reach a critical density where quantum behaviors dominate, creating a superfluid-like state with exotic properties. The concept of fuzzballs, proposed by string theorist Samir Mathur, suggests that black holes are not empty regions with a singularity at the center, but rather balled-up collections of strings that extend throughout the interior of what we perceive as the event horizon. In this picture, there is no singularity at all, just an increasingly tangled ball of strings. Another intriguing possibility is that the interior of a black hole might contain a region of space where the dimensionality changes. Perhaps the three spatial dimensions we're familiar with compress down to 2, 1, or even 0 dimensions at the center. Such dimensional reduction would alter the behavior of matter and energy in profound ways, potentially avoiding the infinities predicted by classical theory. The center of a black hole might also be a place where time itself behaves differently. Some theoretical frameworks suggest that time might branch into multiple possible futures or loop back on itself. Others propose that time might cease to be a fundamental dimension and instead emerge from more basic quantum processes. The fate of consciousness within a black hole presents another fascinating question. If a conscious observer were to fall into a black hole, what would they experience as they approached the center? From the perspective of someone outside the black hole, the falling observer would appear to slow down and freeze at the event horizon, never quite crossing it. But from the observer's own perspective, they would cross the horizon without noticing anything special and continue toward the center. What would consciousness experience in the extreme conditions near the singularity? Would the increasing curvature of space-time affect the neural processes that give rise to awareness? Would quantum effects at the center allow for novel states of consciousness that are impossible under normal conditions? These questions verge on philosophy as much as physics, highlighting how black holes challenge not just our understanding of physical reality, but of experience itself. Some theories propose that the center of a black hole might be a place where the constants of nature change. The strength of gravity, the speed of light, the charge of an electron, all these fundamental parameters might take different values in the extreme conditions at a black hole's core. Such changes would alter the very fabric of reality, potentially allowing for behaviors and structures impossible in our familiar universe. The philosopher Nick Bostrom has proposed the simulation hypothesis, the idea that our perceived reality might be a computer simulation created by an advanced civilization. In this context, some have speculated that the breakdown of physics at a black hole's center might represent the edge of the simulation, a point where the computational resources or programming logic of the simulators reaches its limits. Black holes also challenge our understanding of vacuum. In quantum field theory, empty space is not truly empty, but filled with virtual particles that flicker in and out of existence. Near a black hole's event horizon, these quantum fluctuations lead to Hawking radiation. But what happens to the vacuum state deep inside a black hole, where space-time is severely curved? The physics at a black hole's center might also offer insights into the unification of the four fundamental forces of nature. At extremely high energies, the electromagnetic force, weak nuclear force, and strong nuclear force are believed to merge into a single unified force. Gravity has proven harder to incorporate into this unification, but the conditions at a black hole's center might be where all four forces finally unite, governed by a single set of equations. The presence of extra dimensions, as suggested by some versions of string theory, could dramatically alter what happens at a black hole's center. If our universe has additional spatial dimensions that are normally rolled up too small to detect, they might unfold or become accessible under the extreme conditions of a singularity. Matter falling into a black hole might enter these extra dimensions, appearing to vanish from our three-dimensional perspective, but simply moving into spaces we cannot directly perceive. Even the nature of infinity itself comes into question at a black hole's center. Mathematicians distinguish between different types and magnitudes of infinity, and physicists debate whether physical infinities can exist in reality or are always artifacts of incomplete theories. The apparent infinities at a black hole's singularity might be resolved by understanding that certain types of infinity are physically meaningful while others are not. Throughout history, what seemed like endpoints often turned out to be transitions. The edge of the world became the beginning of a journey to new continents. The emptiness of space became filled with planets, stars, and galaxies. the seemingly indivisible atom opened up to reveal a zoo of subatomic particles. Perhaps the singularity at the center of a black hole represents a similar false endpoint, not a place where reality breaks down, but where it transitions into something our current framework cannot describe. At a black hole's center, this relationship becomes so extreme that a new paradigm may be needed. The very distinction between matter and space-time might blur or dissolve entirely, revealing a more fundamental reality underlying both. If space ends here, perhaps something else begins. Perhaps the center of a black hole is not where things cease to exist, but where they begin to exist differently. Perhaps it is not an endpoint, but a transition, not a boundary, but a bridge. And perhaps through this bridge, new possibilities, even new universes might emerge. As we drift deeper into the theoretical possibilities of black holes, we encounter one of the most captivating ideas in modern cosmology, the concept of bouncing universes. This theory suggests that the apparent endpoint of a black hole might actually be a new beginning, a cosmic bounce, rather than a dead end. The journey to this idea begins with the limitations of Einstein's general relativity. While this elegant theory has proven remarkably accurate in describing gravity and the large-scale structure of the universe, it breaks down in extreme conditions, like those at the center of a black hole or at the moment of the Big Bang. In these scenarios, the mathematics predicts singularities, points of infinite density, where the known laws of physics cease to apply. Many physicists find these singularities troubling. Infinities in physical theories often indicate that something is missing in our understanding. They suggest we need a more comprehensive framework, one that combines general relativity with quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales. This unified theory, often called quantum gravity, remains one of the holy grails of theoretical physics. One approach to quantum gravity, loop quantum gravity, offers a particularly intriguing perspective on what might happen at the center of a black hole. Loop quantum gravity suggests that space-time itself has a discrete quantum structure at the smallest scales, similar to how a smooth flowing stream of water is actually composed of individual water molecules when viewed up close. In this framework, there is a limit to how densely matter can be packed, preventing the formation of a true singularity with infinite density. Instead, when matter collapses beyond a certain density, quantum effects create an outward pressure that counteracts gravity. This resistance leads to what physicists call a bounce. Imagine a rubber ball hitting the ground. It compresses upon impact, storing energy, and then rebounds, converting that stored energy back into motion. Loop quantum gravity suggests that collapsing matter in a black hole might undergo a similar process. As it reaches maximum compression, quantum repulsion causes it to rebound, expanding outward again. But expand into what? This is where the theory takes a truly mind-bending turn. The bouncing matter might not expand back into our universe. Instead, it might create an entirely new space-time region, a baby universe connected to ours only at the moment of the bounce, like a budding yeast cell that grows and then separates from its parent. From our perspective in this universe, we would only see matter falling into the black hole, never to return. We would have no way to observe the bounce or the new universe it creates. But from the perspective of that new universe, the bouncing matter would appear as a tremendous outpouring of energy, perhaps indistinguishable from what we call the Big Bang. This connection between black holes and the birth of universes extends beyond loop quantum gravity. Other approaches to quantum gravity, including certain formulations of string theory, also suggest that the extreme conditions inside black holes might serve as cosmic cradles for new universes. The physicist Lee Smolin has developed this idea into what he calls cosmological natural selection. He proposes that every black hole in our universe might create a new universe, and that these daughter universes might have slightly different physical constants and laws than their parent universes. This introduces a kind of cosmic evolution, where universes that produce more black holes have more offspring. Over time, this could lead to a multiverse dominated by universes particularly good at making black holes. The bounce scenario offers an elegant solution to the problem of singularities. Rather than reaching a point where physics breaks down entirely, matter would transition through a phase of maximum but finite density before expanding again in a new context. The apparent beginning and end points of universes would be connected, creating a continuous cosmic cycle. This perspective transforms how we view black holes. Rather than cosmic dead ends, they become cosmic wombs, giving birth to new realms of existence. The death of a star in our universe might mark the birth of an entire cosmos elsewhere. The mathematics describing this bounce process suggests that the new universe would inherit certain properties from the black hole that created it. The mass and angular momentum of the black hole would influence the initial conditions of the baby universe. In essence, each black hole would pass on a kind of cosmic DNA to its universal offspring. This inheritance might not be perfect. Quantum fluctuations during the bounce could introduce variations, much like genetic mutations in biological reproduction. These fluctuations might alter the strength of fundamental forces or the masses of elementary particles in the new universe. Over many generations of universes, these small changes could accumulate, creating a diverse multiverse of realities, each with its own unique physical laws. If our universe was born from a black hole in another universe, could we find evidence of our cosmic parentage? Some theoretical physicists have suggested that certain large-scale patterns in the cosmic microwave background, the afterglow of the Big Bang, might bear the imprint of the black hole that birthed our universe. However, detecting such signatures remains extremely challenging, if not impossible, with current technology. The bounce scenario also offers a potential answer to one of the most profound questions in cosmology. Why did our universe begin with the particular conditions it did? If our universe emerged from a black hole in another universe, its initial conditions would not be random, but would be determined by the properties of that parent black hole. The apparent fine-tuning of our universe for the emergence of complex structures and life might be explained by this cosmic inheritance. To understand the mechanics of a bounce more deeply, we need to explore the quantum behavior of gravity at extremely small scales. In loop quantum gravity, space-time is not infinitely divisible, but composed of discrete units that cannot be subdivided further, somewhat like pixels in a digital image. These fundamental units, sometimes called atoms of space-time, have a minimum possible size. As matter collapses within a black hole, the density increases until these fundamental units of space-time reach their maximum possible compression. At this point, quantum uncertainty in the geometry of space-time itself creates an effective repulsive force. This quantum repulsion grows exponentially as compression increases, eventually overwhelming even the enormous gravitational attraction and causing the collapse to reverse. In more technical terms, loop quantum gravity describes space-time in terms of spin networks, graph-like structures where each node and link represents a quantum of geometric volume and area. As matter collapses, these spin networks become increasingly interconnected. At maximum compression, they reconfigure into an expanding phase, creating new volumes of space-time. This quantum bounce has been mathematically modeled not just for black holes, but for the entire universe. In the cosmological context, it suggests that our Big Bang might have been preceded by a big crunch in a previous cosmic cycle. The universe would contract until quantum repulsion triggered a bounce, leading to a new expansion phase. Our universe might be just one cycle in an eternal series of expansions and contractions. But the black hole bounce scenario is more intriguing because it suggests not a cyclic universe, but a branching tree of universes. Each black hole in our cosmos could produce a new universe, and each of those universes could contain black holes that produce further universes. Reality would not be a single timeline, but an ever-branching tree of cosmic possibilities. The physicist Nikodem Poplawski has developed a related theory using Einstein-Cartan gravity, an extension of general relativity that incorporates particle spin. In this framework, the enormous tidal forces inside a black hole cause the spin of particles to align, creating a massive torsion in space-time. This torsion acts as a repulsive force, triggering a bounce that inflates the interior of the black hole into a new universe. Poplawski suggests that every black hole in our universe is the doorway to a new cosmos, and that our own universe may be inside what appears to be a black hole in a parent universe. This cosmic nesting doll arrangement could extend indefinitely in both directions, each universe contained within a black hole in a larger universe, and containing black holes that harbor smaller universes. These speculations about universe-creating black holes raise fascinating questions about the conservation of energy and information. If matter and energy from our universe can flow into black holes and emerge as new universes, what happens to the total energy of our cosmos? One answer is that each universe has its own energy budget, conserved within its own boundaries. Matter falling into a black hole in our universe would decrease our cosmic energy, but that same energy would appear in the budget of the new universe being created. As for information, the black hole information paradox takes on new dimensions in the bouncing universe scenario. Perhaps information is not lost when it falls into a black hole, but preserved in the new universe that forms. The patterns and structures of matter in our universe would be transformed but not destroyed, encoded in the initial conditions of the baby universe. Some theories suggest that the bounce process might involve a change in the arrow of time. In our universe, time flows in one direction, from past to future, a direction associated with increasing entropy or disorder. But inside a black hole, approaching the bounce point, time might reach a minimum of entropy before reversing direction. From our perspective, matter falls into a black hole moving forward in time. But from the perspective of the new universe, that same matter might appear to be moving backward in time, emerging from the bounce point to seed the new cosmos. This reversal of time's arrow might explain why the early universe had such low entropy, a puzzle that has long troubled physicists. If our universe formed from a black hole in another universe, its beginning state would naturally have low entropy because it emerged from the highly ordered conditions at the bounce point. The bounce scenario also offers a new perspective on the flatness and homogeneity of our universe, features that are difficult to explain without invoking cosmic inflation, a hypothetical period of exponential expansion in the earliest moments after the Big Bang. If our universe formed through a bounce, the quantum processes involved might naturally create a flat, homogeneous space-time without needing a separate inflationary phase. For a moment, let us imagine what it might be like to experience a black hole bounce from the inside, if such an experience were possible. As matter collapsed toward maximum density, the very notions of space and time would begin to lose meaning. The quantum fluctuations of space-time would become as significant as its average value, creating a foam-like reality where definite locations and moments cease to exist. At the bounce point itself, reality might transition through a state that transcends our usual categories of space and time. It would be a cosmic zero point, a moment of pure potential where the structure of the previous universe has been compressed to its essence and is about to blossom into a new creation. As the bounce initiates, space-time would explode outward in all directions, creating new room for matter and energy to spread out. From the perspective of anything emerging from this process, it would appear as a brilliant flash of creation, the birth of a new cosmos with its own vast horizons of possibility. The bouncing universe theory transforms our understanding of cosmic history from a linear timeline with an absolute beginning and end to an interconnected web of creations and transformations. Each black hole becomes not a cosmic dead end, but a cosmic birth canal, connecting one reality to another in an eternal process of regeneration. This cyclic view of cosmic history has parallels in many ancient philosophical traditions. Hindu cosmology describes cycles of creation and destruction, with each universe emerging from the remains of its predecessor. Norse mythology speaks of successive worlds rising from the ashes of previous ones. The Ouroboros, the snake eating its own tail, appears in many cultures as a symbol of eternal renewal. Modern physics, through the bouncing universe scenario, echoes these intuitions about cosmic recycling in the precise language of mathematical equations. The implications of this theory extend beyond physics into philosophy and even theology. If universes give birth to new universes through black holes, could this process have a beginning? Or has it been happening eternally with no first universe? Does the entire multiverse follow laws that transcend any single universe? Or do even these meta-laws evolve over generations of cosmic reproduction? Some philosophers have noted that the bouncing universe scenario presents a new form of cosmic purpose. While traditional religious views often place purpose and meaning outside the physical world, and scientific materialism tends to see purpose as a purely human construction, the bouncing universe suggests that purpose might be built into the cosmos itself. The purpose of a universe, in some sense, would be to produce black holes that generate new universes, creating an ever-branching tree of realities. For imaginations shaped by Darwinian evolution, the parallels are striking. Just as organisms adapt to their environments through natural selection, producing offspring that inherit their successful traits, universes might evolve to produce black holes efficiently, passing their successful physical laws to their cosmic offspring. Complex structures like galaxies, stars, and potentially life itself might be cosmic adaptations that enhance a universe's reproductive success by increasing its production of black holes. The theory also transforms our place in cosmic history. Rather than being at the midpoint of a linear cosmic timeline, with a single beginning billions of years ago and a heat death trillions of years in the future, we might be part of an eternal process of creation and transformation. The matter in our bodies might have cycled through countless universes, taking different forms in each cosmic iteration. If we could somehow perceive the entire multiverse described by the bouncing universe scenario, we might see not an empty void with isolated bubbles of existence, but a vast cosmic ecology of universes giving birth to universes, each with variations in their fundamental parameters, each exploring different possibilities for the laws of physics, for structure formation, for the emergence of complexity. Where one universe collapses, another might begin. The darkness at the center of a black hole might harbor the first light of a new cosmos. The boundary that seems to mark the end of all paths might actually be the starting line for an entirely different journey, one that unfolds in dimensions and directions we cannot directly perceive or measure from our universe. This cosmic recycling suggests a profound continuity underlying the apparent finality of black holes. Nothing truly ends. Matter and energy are not destroyed but transformed, reborn in new contexts, woven into new stories. The concept of baby universes emerging from black holes evokes a profound metaphor, one that recasts the cosmos not merely as a physical system, but as something almost biological. In this chapter, we explore the fascinating possibility that universes might reproduce through black holes, creating an endless lineage of cosmic offspring. The term baby universe first gained prominence in theoretical physics during the 1980s. Originally, it described tiny bubbles of space-time that might spontaneously form due to quantum fluctuations, each containing its own expanding region of space. These bubbles were thought to quickly disconnect from our universe, becoming separate realities with their own evolutionary paths. But the idea evolved. Physicists began to consider whether these baby universes might not form randomly, but through specific physical processes within our cosmos. Black holes, with their extreme conditions and mathematical peculiarities, emerged as perfect candidates for cosmic reproduction. Imagine our universe as a vast, mature organism. Like any living thing, it contains the potential to create offspring. Black holes, in this view, are not anomalies or deadly traps, but reproductive organs, places where the universe channels its creative potential to birth new realities. When a massive star collapses to form a black hole, matter compresses beyond what our current physics can describe. At this boundary of understanding, new possibilities emerge. Perhaps the collapsing core doesn't simply crush to a mathematical point, but punches through to another dimension or state, carrying with it the seeds of a new cosmos. From our external perspective, we see only matter disappearing beyond the event horizon. But within, that same matter might be undergoing a transformation, its energy and information reconfiguring into the building blocks of a new universe with its own space-time. The Russian cosmologist Andrei Linder, one of the architects of cosmic inflation theory, has proposed models where baby universes form not just from black holes, but from high-energy density fluctuations in the very early universe. These baby universes would initially connect to our universe through tiny wormholes before separating to become independent realities. Black holes might represent a similar process occurring not just in the early cosmos, but throughout cosmic history. If this view is correct, our universe might itself be a baby universe, born from a black hole in a parent universe. That parent, in turn, might have emerged from a grandparent universe, and so on, creating a cosmic family tree stretching back through generations of universal ancestors. This perspective provides a new approach to the puzzle of cosmic origin. Rather than the universe appearing from nothing in the Big Bang, an idea that has always strained both physics and philosophy, it might have emerged from a pre-existing reality through a black hole. The Big Bang would not be the absolute beginning, but a transition, a birth event connecting our universe to its cosmic parent. What would this parent universe be like? Would it operate under the same physical laws as our own? The physicist Lee Smolin suggests that baby universes might inherit most physical characteristics from their parents, but with small variations, similar to genetic mutations in biological reproduction. These variations would affect fundamental constants like the strength of gravity, the mass of elementary particles, or the ratio of dark energy to normal matter. Over many generations of cosmic reproduction, these small changes would accumulate, creating a diverse multiverse of realities, each with slightly different physical parameters. Some of these variations would lead to universes that produce black holes more efficiently than others. Those prolific universes would generate more cosmic offspring, leading to a kind of natural selection among universes. This cosmic natural selection offers a tantalizing explanation for the apparent fine-tuning of our universe. The physical constants in our cosmos seem exquisitely calibrated to allow for the formation of complex structures like galaxies, stars, and ultimately, life. Traditional explanations invoke either extraordinary cosmic coincidence, an intelligent designer, or the existence of countless random universes, most of which are sterile and lifeless. But cosmic natural selection suggests a different answer. If black holes are the reproductive mechanism for universes, then physical parameters that lead to abundant black hole formation would be favored over many generations. Interestingly, many of the same conditions that allow for plentiful black holes, like the existence of stable stars, also create environments where complexity and potentially life can emerge. In this view, our universe is hospitable to life, not by random chance or design, but because its physical laws evolved through cosmic generations to maximize black hole production, inadvertently creating conditions where stars burn steadily for billions of years, where heavy elements form in supernovae, and where complex chemistry can unfold on the surfaces of rocky planets. The process mirrors biological evolution in striking ways. Just as organisms adapt to their environments through natural selection, passing on traits that enhance survival and reproduction, universes might evolve to produce black holes efficiently, passing their successful physical laws to their cosmic offspring. The result would be a multiverse dominated by universes particularly good at making black holes, just as Earth's biosphere is dominated by organisms particularly good at reproducing in their specific ecological niches. This evolutionary perspective transforms how we see cosmic history. Rather than being a singular event unfolding in isolation, our universe becomes part of a vast, interconnected family of realities, each giving birth to others in an eternal process of cosmic reproduction. Consider the mathematics of this process. A single universe with physical laws conducive to black hole formation might produce billions or even trillions of black holes during its lifetime. Each black hole could potentially give birth to a new universe. Some of these daughter universes would inherit variations, making them even better at producing black holes, leading to an exponential growth in the cosmic family tree. Over many generations, universes that produce few or no black holes would become cosmic dead ends, while prolific universes would dominate the multiverse population. The result would be a kind of cosmic optimization, with the process gradually selecting for physical laws that maximize black hole production, while still allowing for the complex structures needed to form stars and galaxies. This process would be blind, without foresight or purpose in the conventional sense. Like biological evolution, it would proceed through a simple algorithm, varying parameters and selecting outcomes that enhance reproduction. Yet over time, it might create universes of astonishing complexity and richness. The theory also offers a striking perspective on cosmic death. In traditional cosmology, universes face a bleak fate, either endless expansion into cold, empty space, or a catastrophic big crunch where everything collapses back to a singularity. But if universes reproduce through black holes, cosmic death becomes less final. A universe might eventually become cold and sterile, but its legacy would continue through the baby universes it spawned during its active phase, each carrying variations of its physical laws forward into new cosmic cycles. This reproductive process would be asymmetric. A parent universe could create many offspring, but those offspring would not directly influence their parent. Information would flow forward in one direction across generations. This one-way flow of cosmic inheritance explains why we cannot directly observe or interact with our parent universe, even though its characteristics might be encoded in our physical laws. The bubble universes formed through this process would initially be microscopic, perhaps smaller than an elementary particle. But they would contain all the energy that fell into the black hole that birthed them, channeled into a new dimensional framework. Like cosmic seeds, they would unfold and expand, potentially growing into realities as vast and complex as our own. This growth would occur in a dimensional direction inaccessible from the parent universe. The baby universe would not expand into the space of its parent, but would create its own space-time, connected to the parent universe only at the singular point of its birth, like a branch growing from a tree trunk. Some mathematical models suggest these baby universes might maintain a tiny connection to their parent universe, a kind of cosmic umbilical cord in the form of a wormhole. However, most theoretical frameworks indicate this connection would be severed almost immediately, leaving the baby universe to evolve in complete isolation from its cosmic parent. Without direct observational evidence, the baby universe theory remains speculative, but it has gained attention because it addresses several stubborn puzzles in physics and cosmology. It offers a natural explanation for the origin of our universe without requiring something to emerge from nothing. It accounts for the apparent fine-tuning of physical constants without invoking chance or design, and it provides a framework for understanding black holes, not as cosmic anomalies, but as integral parts of a larger cosmic process. The theory also has philosophical implications. If universes reproduce through black holes, then the cosmos as a whole would display a kind of immortality, even as individual universes are born and eventually die. The matter and energy that constitute our reality would cycle endlessly through generations of universal offspring, taking new forms in each iteration. For conscious beings like ourselves, this cosmic reproduction offers a new perspective on our place in reality. While we cannot personally survive the death of our universe, the matter that composes us and the fundamental patterns of our existence might be carried forward into new cosmic contexts. Our atoms might one day form part of a star in a descendant universe, perhaps even becoming incorporated into new forms of life. The baby universe theory also challenges our notions of cosmic uniqueness. If our universe is one of many in a vast family tree of realities, we are not alone in the largest sense, even if we never contact other intelligent life within our observable cosmos. Beyond the limits of our perception, other universes may harbor their own stars, planets, and perhaps even observers, each experiencing their own version of reality, shaped by slightly different physical laws. This cosmic pluralism echoes the Copernican revolution that removed Earth from the center of the universe and the Darwinian insight that humans are one branch on the tree of terrestrial life. Once again, we are asked to expand our perspective, to see our reality not as unique or central, but as one instance in a vast tapestry of cosmic possibilities. Yet the theory also suggests a kind of cosmic meaning. If universes evolve to produce black holes more efficiently, and our universe has physical laws particularly suited to this process, then we exist in a cosmos optimized through many generations of universal reproduction. The same conditions that allow for our existence, like stable stars and complex chemistry, might be cosmic adaptations that enhance our universe's reproductive potential. In this light, black holes take on a new significance. They are not just destructive phenomena or astronomical curiosities, but cosmic cradles, the wombs where new universes gestate before emerging into independent existence. The supermassive black holes at the centers of galaxies might be the most prolific cosmic parents, potentially giving birth to universes with greater mass and energy than those spawned by stellar black holes. The matter falling into these cosmic wombs carries with it all the complexity and structure of our universe, all the patterns formed over billions of years of cosmic evolution. This information becomes the seed pattern for a new reality, a cosmic inheritance passed from parent to child across the generations of universal reproduction. From an observational perspective, could we ever confirm the baby universe theory? Unfortunately, direct evidence would be extraordinarily difficult to obtain. Baby universes would be causally disconnected from our reality, making direct observation impossible. However, indirect evidence might eventually support or challenge the theory. Advances in understanding quantum gravity could reveal whether the conditions inside black holes allow for the kind of bounce or transition the theory proposes. Cosmological observations might uncover patterns in our universe, suggesting an origin in a black hole from another reality, and mathematical models might demonstrate whether cosmic natural selection would indeed lead to universes with physical parameters like our own. For now, the baby universe theory remains a tantalizing possibility, a framework that transforms our understanding of black holes from cosmic destroyers to cosmic creators. It suggests that the darkness at the center of a black hole might harbor the seeds of new light, new space, new time, new possibilities. Creation doesn't end with stars. It continues in the darkness between them. The cosmic story is not a linear progression from birth to death, but an eternal branching, a tree of universes growing through the metaphysical soil of existence. Each black hole we observe might be nurturing a universe within, preparing to add another branch to the cosmic tree, another chapter to the endless story of reality. As we delve deeper into the cosmic possibilities of black holes as universe generators, we must expand our perspective beyond a single universe. The concept of a multiverse, a vast collection of universes, each with potentially different physical laws, has moved from science fiction to serious scientific inquiry over recent decades. Within this broader framework, black holes take on an even more profound significance as connectors or creators of alternate cosmic realities. The multiverse hypothesis comes in several variations, each with different implications for how reality might be structured beyond our observable cosmos. The simplest version proposes that our universe extends infinitely beyond what we can see, with matter eventually reconfiguring in every possible arrangement given enough space. This would create distant regions identical or nearly identical to our own, effectively parallel universes within the same spacetime. A more complex version emerges from inflation theory, which describes an extremely rapid expansion of spacetime in the earliest moments of cosmic history. Many cosmologists now believe that inflation doesn't end everywhere at once, but continues eternally in some regions while stopping in others. This creates a cosmic landscape of bubble universes, each one a region where inflation has stopped, allowing matter and energy to condense into stars and galaxies. String theory, which attempts to unify all fundamental forces, including gravity, suggests yet another multiverse model. According to this framework, the equations of physics might have an enormous number of possible solutions, perhaps 10 to the power of 500 or more. Each solution would describe a universe with different physical laws, different particles, different fundamental forces, and different dimensions. Our universe would be just one solution among this vast landscape of possibilities. Black hole universe genesis provides a mechanism that could connect these various multiverse models. If black holes can indeed create new universes, then each universe in the multiverse could be linked to others through these cosmic portals. Rather than being isolated bubbles, universes would form an interconnected network or family tree, with parent universes giving birth to children through black holes. Let us explore this possibility more deeply. Imagine a vast cosmic family tree, where each branch represents a universe. At certain points along each branch, smaller branches emerge, representing baby universes born from black holes. Some of these new branches might be stunted, representing universes with physical laws that don't allow for complexity or long-term stability. Others might branch prolifically, representing universes particularly fertile in creating their own black holes and thus their own cosmic offspring. Our universe would be one branch on this cosmic tree. We cannot see the trunk or the other branches from our position, but we can infer their existence from the theoretical implications of our physical laws. The trunk of this tree might extend indefinitely into the cosmic past, with no absolute beginning, only an endless chain of universe births. Or perhaps there was an original seed universe, formed through some other process that began the chain of cosmic reproduction. This first universe might have had only a crude approximation of our physical laws, but over many generations of universal offspring, these laws evolved and refined through cosmic natural selection, eventually producing universes like our own that excel at generating black holes. This evolutionary process would not require consciousness or intention. Like biological evolution on Earth, it would operate through the simple algorithm of variation and selection. Small differences in the physical constants and laws between parent and child universes would create variation. Universes better at producing black holes would create more offspring, naturally selecting for those physical traits over many generations. But what would cause these variations in physical laws between parent and child universes? Several mechanisms have been proposed. One possibility involves quantum fluctuations at the moment of universe birth. Just as quantum indeterminacy creates small uncertainties at the subatomic level in our universe, it might create small differences in the fundamental constants of a baby universe compared to its parent. Another possibility comes from the specific conditions inside the black hole that births a new universe. Different black holes have different masses, different amounts of electric charge, and different rates of rotation. These properties might influence the characteristics of the baby universe that emerges, creating a correspondence between black hole properties in the parent universe and fundamental constants in the child universe. The anthropic principle offers yet another perspective on this cosmic variation. This principle notes that we should not be surprised to find ourselves in a universe compatible with our existence, regardless of how rare such universes might be in the larger multiverse. If most universes are hostile to complex structures or life, observers like us would naturally find themselves in one of the rare universes where complexity can emerge. Combined with black hole universe genesis, this suggests an intriguing possibility. Perhaps universes that produce observers like us are also particularly good at producing black holes. This correlation would arise if the same physical conditions that allow for stable stars, complex chemistry, and potentially life are also conditions that lead to abundant black hole formation. For instance, a universe needs stars to create black holes. Stars also provide the stable energy sources and the nuclear synthesis of heavy elements necessary for complex chemistry and potentially life. A universe without stars would produce neither black holes nor observers. Similarly, a universe where stars burn too quickly or too slowly might be suboptimal for both black hole production and the emergence of complexity. This correlation, if it exists, would explain why we find ourselves in a universe so apparently fine-tuned for our existence. It would not be coincidence or design, but the result of cosmic evolution, selecting for universes proficient at reproduction through black holes, inadvertently creating conditions where observers can evolve. The theoretical physicist Lee Smolin has developed this idea into a comprehensive framework he calls cosmic natural selection. In this view, black holes function as universe replicators, and physical parameters evolve to maximize black hole production. After many generations, the multiverse would be dominated by universes with physical laws similar to our own, not because our laws are special in an absolute sense, but because they are particularly effective at propagating themselves through black hole reproduction. This framework makes a bold prediction. If our universe has been optimized through cosmic natural selection to produce black holes, then small changes to the fundamental constants of nature should generally reduce rather than increase black hole production. Smolin has argued that this prediction holds true based on our current understanding of physics, though the complexity of the calculations leaves room for debate. Another consequence of the black hole multiverse would be the potential for vastly different physical laws in other cosmic realms. The universes most closely related to ours, our cosmic siblings or close descendants, might have physical laws only slightly different from our own, but distant branches of the cosmic family tree might operate under radically different principles. Imagine universes with different numbers of spatial dimensions, different fundamental forces, different elementary particles. Some might have no equivalent to electromagnetism, but 2 or 3 types of gravitational force. Others might have additional spatial dimensions beyond the 3 we experience. Some might operate under completely different mathematical frameworks that we can barely conceptualize with our minds evolved in this particular cosmic context. Most of these variant universes would likely be sterile, unable to form stable structures or reproduce through their own black holes. They would be cosmic dead ends in the evolutionary tree. But some might develop their own complex structures, and perhaps even their own forms of observers, utterly unlike anything in our universe, but equally capable of asking questions about their cosmic origin. This vision of cosmological diversity challenges our conception of physical laws as absolute and universal. What we call the laws of nature might be more like local bylaws, applicable in our cosmic neighborhood, but different elsewhere in the greater multiverse. The true meta-laws, the principles governing how universes are born and how they vary, might operate at a higher level than anything we can directly observe from within our single universe. The multiverse generated through black holes would have a branching, tree-like structure rather than existing as parallel realities side by side. Each universe would be causally disconnected from its siblings, but connected to its parent and children through the black hole birthing process. Information and causality would flow in one direction, from parent to child, creating a cosmic arrow of time at the multiverse level. This directional flow of cosmic inheritance explains why we cannot directly observe or interact with our parent universe or our cosmic siblings. They exist in different space-time continua, connected to us only through the one-way process of universe birth. The black hole that created our universe is long gone from the perspective of our parent reality, and the black holes in our universe are creating new offspring that we cannot observe or contact. Yet despite this causal disconnection, all universes in the family tree would share a common cosmic heritage. The fundamental patterns of our reality would echo those of our ancestors, modified through small variations across generations. We would be part of a vast cosmic lineage, carrying forward patterns of existence that have proven successful at reproduction through countless universal generations. The black hole multiverse also offers a new perspective on cosmic beginnings and endings. Rather than a single Big Bang creating everything from nothing, we would have countless births and rebirths, each black hole initiating a new cosmic cycle. Our own Big Bang would be just one such birth event, the moment when our universe emerged from the collapse of matter in a black hole in our parent universe. Similarly, the far future of our universe would not be an absolute end, but a transition. As stars burn out and matter either disperses into the void or collapses into black holes, our universe would gradually lose its ability to form new structures or create new black holes. But its legacy would continue through the universes it spawned during its active phase, each carrying forward variations of its physical patterns into new cosmic cycles. From a philosophical perspective, this endless branching of cosmic reality transforms how we might view existence itself. Reality would not be a single timeline with an absolute beginning and end, but an ever-growing tree of possibilities, each branch exploring different physical laws and different pathways for structure and complexity to emerge. The total creative potential of this multiverse would be vastly greater than that of a single universe, no matter how large. A single universe, even if infinite in spatial extent, would be constrained by one set of physical laws. But the multiverse would explore countless variations of these laws, testing every possible configuration of reality that can sustain itself and reproduce. This cosmic exploration happens blindly, without foresight or intention, through the simple mechanism of variation and selection. Yet over countless generations, it might discover arrangements of physical law that allow for remarkable complexity, for stable structures at multiple scales, for rich interactions between matter and energy, for the emergence of self-organizing systems and potentially consciousness. Our universe, with its galaxies and stars, planets and living things, minds and cultures, would be one product of this vast cosmic experiment, one branch of the tree that happened to discover a particularly fertile configuration of physical law. We are not the purpose of this process, but we are one of its most remarkable outcomes, conscious structures capable of looking back and glimpsing, however dimly, the greater cosmic story of which we are a part. The black hole multiverse also offers a new framework for thinking about the uniqueness or commonality of complex structures like life. In a single universe with one set of physical laws, the emergence of life might seem like an extraordinary stroke of cosmic luck, requiring a precise balance of numerous factors. But in a vast multiverse exploring countless variations of physical law through black hole reproduction, the emergence of some form of complexity becomes almost inevitable. Some branches of the cosmic tree would develop physical laws allowing for information processing systems that we might recognize as alive, though perhaps utterly different from Earth life in their fundamental chemistry and organization. Other branches might develop forms of complexity we can barely imagine, operating under physical principles with no clear analog in our universe. From this perspective, we are not alone in the largest sense, even if we never encounter other intelligent life within our observable universe. Beyond the limits of our cosmic horizon, beyond even the boundaries of our particular universe, the multiverse would likely contain countless other forms of complexity, other types of observers, other participants in the great cosmic story. Yet communication or travel between universes in this multiverse would likely be impossible. Unlike science fiction depictions of parallel worlds that characters can move between, the universes born from black holes would be causally disconnected, except for the one-way flow of information from parent to child at the moment of cosmic birth. We could never visit or even observe our cosmic siblings or our parent universe. This isolation has philosophical implications. Each universe in the multiverse would be effectively alone, unable to exchange information with others. Each would develop its own cosmic history, its own structures, its own forms of complexity, all evolving in isolation from the rest of the multiverse. Yet all would be connected through their shared cosmic lineage, all branches of the same greater tree of reality. For conscious observers like ourselves, contemplating the black hole multiverse offers a strange blend of cosmic insignificance and significance. On one hand, our universe is just one among countless others, not unique or central to the greater cosmic story. On the other hand, we are participants in an extraordinary process, a vast cosmic exploration of possibility that has, in our branch of the tree, discovered conscious structures capable of glimpsing the larger pattern. The multiverse concept transforms traditional questions about cosmic purpose. In a single universe, the absence of an external designer often seems to imply an absence of purpose altogether. But in a multiverse shaped by variation and selection, purpose emerges from the process itself. The blind algorithm of cosmic evolution leads to universes increasingly capable of reproduction through black holes, inadvertently discovering physical laws that allow for remarkable complexity along the way. This purpose is not conscious or intentional in the conventional sense, but emerges from the simple mechanism of differential reproduction. Universes better at making black holes have more cosmic offspring, gradually populating the multiverse with realities skilled at both reproduction and the generation of internal complexity. Our existence as conscious observers might be a side effect of this process, but it is not a random accident either. Instead, we might be the product of countless generations of cosmic evolution, each refinement of physical law bringing the multiverse one step closer to configurations that allow for the emergence of structure, complexity, and eventually consciousness. We are not the goal of this process, but we are one of its most remarkable features, the multiverse looking at itself through conscious structures that have evolved within it. The black hole genesis theory also raises profound questions about information and meaning across cosmic generations. As matter falls into a black hole in our universe, it carries with it all the complexity and structure, all the patterns and information it has developed. In the transition to a new universe, how much of this information is preserved? Does the child universe inherit not just basic physical parameters from its parent, but some echo of the specific structures that existed there? Some theoretical models suggest that the inheritance is fairly general, with the broad physical parameters being passed down, but the specific configurations being lost in the transition. Others propose that some trace of the parent universe's specific structures might be encoded in the initial conditions of the child universe, like a cosmic memory passed down through the generations. This question connects to deeper issues about the nature of information and its conservation across cosmic transitions. If information is truly fundamental, as many physicists now believe, then perhaps it cannot be destroyed even in the extreme conditions of a black hole singularity. Instead, it might be transformed and passed on to the next cosmic cycle, creating a thread of informational continuity across the generations of universal offspring. For conscious observers, this possibility hints at a form of cosmic legacy. While we as individuals cannot survive the death of our universe, the patterns we create during our lives, the information we generate and process, might in some highly transformed way influence the initial conditions of future universes. Our actions would not exactly be remembered, but they would leave some trace in the cosmic inheritance. Perhaps every black hole we see is a doorway to a cosmos unlike our own. Perhaps the darkness we perceive hides the birth of countless new lights, new spaces, new times, new possibilities unfolding in dimensions we cannot access. And perhaps our own universe carries within it the echo of its cosmic parent, the inheritance of a reality we can never directly observe, but whose patterns continue through us in endlessly creative variations. Having explored the philosophical and theoretical landscape of black holes as universe generators, we now turn to a more concrete question. How might this process actually work? What physical mechanisms could transform the death of a star in one universe into the birth of an entire cosmos in another dimension? While we remain in the realm of theoretical physics, several frameworks offer potential pathways for this extraordinary transition. One of the most developed explanations comes from a field of physics called brane theory, an extension of string theory. In this framework, our universe exists on a multidimensional membrane, or brane, floating within a higher dimensional space called the bulk. Other branes might exist within this same bulk, effectively parallel universes that we cannot directly observe or interact with because we are confined to our own brane. Black holes, with their extreme gravitational fields, might create distortions that extend beyond our brane into the bulk. The singularity at a black hole's center could puncture our brane, creating a tunnel through the bulk that extends outward into a new region of space-time. Matter falling into the black hole would travel through this tunnel, emerging in a new cosmic domain. The mathematics of this process draws on complex aspects of string theory and quantum gravity. In certain formulations, the interior of a black hole undergoes a process analogous to quantum tunneling, where a particle passes through an energy barrier that classical physics would deem impenetrable. The collapsing matter tunnels through a barrier in the fabric of space-time itself, emerging in a new dimensional context. This tunnel would be different from the hypothetical wormholes that connect two regions within the same universe. A black hole universe generator would create a passage to an entirely new space-time, disconnected from our own except at the point of creation. The tunnel itself might exist only momentarily, long enough for the transfer of matter and energy before sealing off, leaving the baby universe to evolve in isolation. The concept of extra dimensions is crucial to understanding how this process might work. In our everyday experience, we perceive 3 spatial dimensions and 1 time dimension. But string theory suggests that reality might contain 6 or 7 additional spatial dimensions, curled up so tightly that we cannot directly perceive them. These hidden dimensions would be present throughout our universe, including within black holes. As matter collapses into a black hole, the extreme density might cause these extra dimensions to unfold or expand in the central region. This dimensional expansion would create new space, not within our universe, but perpendicular to it in a higher dimensional sense. The matter falling into the black hole would flow into this newly created space, seeding the formation of a new cosmic domain. The process bears some mathematical similarity to cosmic inflation, the extremely rapid expansion that cosmologists believe occurred in the earliest moments of our universe. In both cases, a small region of space-time expands exponentially, but whereas inflation occurred within our universe, expanding existing space, a black hole would generate entirely new space in dimensions orthogonal to our own. Another approach to black hole universe generation comes from loop quantum gravity, which describes space-time as a network of tiny loops or quantized units of volume. In this framework, a black hole singularity would reach a critical density where quantum gravitational effects create a repulsive force, causing the collapsing matter to bounce and expand outward again. But this expansion would not occur back into our universe. Instead, it would create a new branch of space-time, connected to our universe only at the bounce point. The physicist Nikodem Poplawski has developed a related model using Einstein-Cartan theory, an extension of general relativity that incorporates the quantum property of spin. When matter collapses into a black hole, the alignment of particle spins creates a torsion in space-time, a twisting that resists further compression. This torsion eventually leads to a bounce that inflates the interior of the black hole into a new universe. In Poplawski's view, every black hole in our universe contains a baby universe, and our own universe might exist inside a black hole in another, larger universe. This nesting of universes within black holes could extend indefinitely in both directions, creating a cosmic structure reminiscent of Russian nesting dolls. A different perspective comes from the holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary. Applied to black holes, this principle indicates that everything falling into a black hole gets encoded on its event horizon rather than actually reaching the singularity. Some theoretical physicists have proposed that this encoded information might be projected into a new dimensional framework, creating a holographic universe derived from the collapsed matter. This process would be analogous to how a two-dimensional hologram can encode and project a three-dimensional image. The event horizon of a black hole would encode the complete quantum state of everything that fell into it, and this information would be projected or decoded into a new space-time, creating a universe holographically generated from the information on the black hole's boundary. The physicist Leonard Susskind has developed a related concept called black hole complementarity, which suggests that from an outside perspective, information never crosses the event horizon but remains encoded on it, while from the perspective of someone falling in, they pass through the horizon normally and experience whatever lies beyond. These seemingly contradictory descriptions might be reconciled if the interior of the black hole creates a new universe with its own independent reality. At an even more speculative level, some theoretical physicists have proposed that the laws of thermodynamics might play a crucial role in black hole universe generation. A black hole represents a state of extremely high entropy or disorder from the perspective of our universe, as all the distinctive structures of the matter falling in seem to be erased, converted into just three parameters: mass, charge, and angular momentum. But what appears as high entropy from our perspective might represent low entropy from another perspective. The seeming disorder of a black hole might be reinterpreted as the highly ordered initial state of a new universe. The black hole would function as a cosmic reset, transforming the aged, high-entropy matter of our universe back into a low-entropy state that can seed the birth of a new cosmos. This thermodynamic perspective connects to questions about the arrow of time. In our universe, time flows in the direction of increasing entropy, from ordered states to more disordered ones. But if a black hole can convert high-entropy matter into the low-entropy initial conditions of a new universe, it might effectively reverse the arrow of time, creating a new temporal sequence flowing from the endpoint of our universe. From a collapsing star's perspective, the process of black hole universe generation would unfold as a continuous sequence of events. As the star's core implodes beyond the density of nuclear matter, it would enter a realm where conventional physics breaks down. The core would continue to contract until it reached a critical threshold where quantum gravitational effects become significant. At this point, several possibilities open up. In some models, the core would reach a state of maximum compression before bouncing outward, not back into our universe, but into a newly created space-time domain. In others, the collapsing core would tunnel through a barrier in the fabric of reality, emerging in a different dimensional context. In yet others, the information encoded on the forming event horizon would be projected into a new framework, generating a universe holographically. Whichever mechanism applies, the result would be the same from our external perspective. We would see matter disappearing beyond the event horizon, seemingly lost to our universe forever. But from the perspective of that same matter, it would be entering a dramatic new phase, becoming the primordial material for an entire cosmos. The initial moments of this baby universe would likely resemble what we call the Big Bang, a state of extremely high density and temperature expanding rapidly outward. The physical laws governing this new universe would be determined largely by the properties of the parent black hole and the specific mechanics of the generation process. If the black hole had particular quantum characteristics, these might translate into specific values for fundamental constants in the baby universe, setting the strength of gravity, the masses of elementary particles, and other basic parameters. Small quantum fluctuations during the formation process might introduce variations from the parent universe's physical laws, creating a unique cosmic identity for the new reality. The initial expansion would be driven by the enormous energy concentrated in the collapsing core. As this energy spread out through the newly created space, it would gradually cool and condense, eventually forming elementary particles, atoms, stars, and galaxies through processes broadly similar to those in our own cosmic history. From the perspective of anything within this new universe, there would be no observable connection to the parent universe. The only evidence of its cosmic origin might be encoded in its fundamental physical laws and the large-scale patterns of its earliest structures. The boundary where it connected to its parent universe would appear, if it could be observed at all, as the earliest moment of cosmic time, what we call the Big Bang. This model of cosmic reproduction raises intriguing questions about conservation principles across universe transitions. In our universe, we observe that quantities like energy, momentum, and certain quantum numbers are always conserved, never created or destroyed, but only transformed. Would these conservation laws apply across universe boundaries? Some theoretical frameworks suggest that the total energy of a baby universe would equal the mass energy equivalent of everything that fell into the black hole that created it, maintaining conservation across the generation event. Others propose that conservation principles might apply within each universe, but not necessarily across the boundary between parent and child cosmos. The topology, or overall shape and connectivity, of a baby universe would likely differ from its parent. While our universe appears to be flat and possibly infinite in spatial extent, a universe born from a black hole might have a more complex geometry, perhaps being closed and finite while still expanding. The specific topology would depend on the mechanics of the generation process and could influence the long-term evolution of the baby cosmos. The role of time in this process presents particular challenges to our understanding. From our perspective in the parent universe, the formation of a black hole and the disappearance of matter beyond its event horizon are events in time, occurring at specific moments in our cosmic history. But the baby universe generated from this black hole would have its own time dimension, its own cosmic clock starting from its birth moment. This creates a curious temporal relationship between parent and child universes. A black hole forming in our universe billions of years after the Big Bang might generate a baby universe with its own multi-billion-year history. From the perspective of that baby universe, its entire existence, including the evolution of any life or consciousness within it, would be contained within what we would perceive as the interior of a black hole at a particular moment in our time. The transition from a collapsing star to an expanding universe involves a profound shift in perspective. From outside the black hole, we see matter converging toward a central point, but from inside the baby universe, we would see matter expanding outward in all directions. This inversion of geometric perspective, from collapse to expansion, represents one of the most counterintuitive aspects of black hole universe generation. One way to visualize this inversion is to imagine the interior of the black hole as a region where space and time effectively trade roles. Outside the event horizon, time flows forward and space extends outward. But inside, what was the time direction becomes a space direction in the baby universe, and a space direction from our universe becomes the time direction of the baby universe. This dimensional reorganization would transform the inward collapse into an outward expansion when viewed from within the new cosmic framework. The physicist and philosopher Quentin Smith has suggested an even more radical possibility, that our own Big Bang might have been precisely such an inversion. In this view, what we perceive as the beginning of our universe would be the time-reversed image of a collapse in another cosmos. Each black hole ending would appear from the other side as a Big Bang beginning. This perspective transforms our understanding of black holes from cosmic endpoints to cosmic transitions, from places where matter and information are destroyed to places where they are transformed and reborn in new contexts. A black hole would not be where things cease to exist, but where they begin to exist differently. The generation of a universe from a black hole would not be instantaneous, but would unfold as a process. The collapsing matter would pass through stages of increasing density and curvature before reaching the critical threshold where the transition to a new universe occurs. This process might take only fractions of a second from the perspective of the collapsing matter, but could appear frozen in time from the external viewpoint due to the extreme gravitational time dilation near the event horizon. Within the emerging baby universe, the initial conditions would be set by the properties of the parent black hole, but the subsequent evolution would follow its own course, potentially developing structures, systems, and even forms of consciousness utterly unlike anything in the parent cosmos. Each universe would be an independent experiment in reality, testing different combinations of physical laws and initial conditions to see what forms of complexity might emerge. What we call a collapse may look like creation from the other side. The death of a star in our universe might be the birth cry of a cosmos elsewhere. The darkness that swallows light in a black hole might be the first illumination of a new reality. The ending that we perceive might be a beginning perceived by others, in a cycle of cosmic renewal that transcends the limits of any single universe. Having explored how black holes might create new universes, we now turn to a provocative question. Could our own universe have been born from a black hole in another cosmos? Could the Big Bang, that moment of creation that birthed our reality, actually represent the interior view of matter collapsing into a black hole in a parent universe? This possibility, once considered speculative even by theoretical physics standards, has gained increasing attention as researchers note the striking similarities between black hole formation and the birth of our cosmos. The Big Bang and black holes share several profound features that hint at a possible connection. Both involve singularities, points where our current understanding of physics breaks down. Both include regions of incredible density and energy. Both involve rapid expansion from the perspective of anything on the inside. And both create boundaries that prevent information from crossing between regions of space-time. Let us examine these parallels more carefully. The standard model of cosmology describes our universe as emerging from an incredibly hot, dense state about 13.8 billion years ago. In the earliest moments, all matter and energy were compressed into a volume smaller than an atom, with temperatures and densities beyond our ability to simulate even with the most advanced physics. From this initial state, the universe rapidly expanded and cooled, eventually forming the stars, galaxies, and planets we observe today. Black holes form when matter collapses beyond a critical density, creating a singularity surrounded by an event horizon. Within this boundary, space becomes so severely curved that all paths lead inward toward increasing density. From the perspective of an external observer, time appears to slow and eventually freeze for anything approaching the horizon, while from the perspective of something crossing the horizon, passage occurs without any dramatic local effects. The physicist Nikodem Poplawski has developed one of the most detailed frameworks connecting these phenomena. Using Einstein-Cartan theory, which extends general relativity to include the quantum property of particle spin, he suggests that every black hole contains a baby universe, and our own cosmos exists inside a black hole in a parent universe. The Big Bang would represent the other side of a black hole collapse, viewed from within. In this model, when matter falls into a black hole and reaches extreme density, the alignment of particle spins creates a torsion in space-time. This torsion generates a repulsive force that counters gravitational collapse, causing the matter to bounce and expand outward into a new space-time region. From inside this region, which we would call a universe, the bounce would appear as a Big Bang, the beginning of an expanding cosmos. The mathematics of Einstein-Cartan theory predicts that this process would create a universe with properties similar to our own, including an inflationary period in its earliest moments. The repulsive force generated by torsion could drive an exponential expansion of space, explaining the extreme flatness and uniformity we observe in our cosmos without requiring additional theoretical mechanisms. If our universe does exist inside a black hole, the boundary of this black hole would correspond to what we perceive as the beginning of time. The event horizon would appear not as a location in space, but as a moment in time, the earliest instant of cosmic history. Beyond this temporal boundary, we cannot see or interact, just as nothing inside a black hole can communicate with the external universe. This perspective resolves one of the most puzzling features of the Big Bang, its apparent creation of space and time from nothing. In the black hole universe model, our cosmos didn't emerge from nothing but from the collapse of matter in a parent universe. The beginning of our time would be connected to a particular moment in the parent universe's time, when matter fell into the black hole that birthed our reality. The total mass energy of our universe would correspond to the mass energy of everything that fell into the parent black hole. The conservation principles that physicists hold sacred would be maintained across the cosmic boundary, with nothing truly created or destroyed, but only transformed from one context to another. This model also addresses the mystery of our universe's extreme flatness and homogeneity. In standard cosmology, these features are explained by a period of cosmic inflation in the earliest moments after the Big Bang, when space expanded faster than light speed. The black hole universe theory suggests that this inflation could be a natural consequence of the bounce process, with torsion driving an exponential expansion as the baby universe emerges. The physicist Lee Smolin has explored another aspect of this connection, suggesting that a process of cosmic natural selection would tend to produce universes with physical parameters similar to our own. If universes reproduce through black holes and small variations in physical laws occur during reproduction, then over many generations the multiverse would become dominated by universes particularly good at making black holes. Intriguingly, many of the same conditions that allow for plentiful black hole formation also create environments where stable stars, complex chemistry, and potentially life can emerge. These include the strength of the fundamental forces, the masses of elementary particles, and the cosmological constant that determines the universe's expansion rate. All these parameters in our universe seem calibrated to allow both black hole formation and the emergence of complexity. If our universe was born from a black hole, its physical laws might represent slight variations from those of its parent cosmos, modifications that have proven particularly effective at generating its own black holes and thus its own cosmic offspring. We would be living in a universe optimized through many generations of cosmic reproduction to produce both black holes and the complex structures that emerge along the way. This connection between black holes and the Big Bang transforms our understanding of cosmic history from a linear timeline with an absolute beginning to a branching family tree of universes, each emerging from black holes in their parent cosmos. Our Big Bang would not be the beginning of everything, but merely the beginning of our branch of the greater multiverse. The evidence for this connection remains indirect. We cannot observe beyond our cosmic horizon, much less peek outside our universe to see the black hole that might have birthed it. But several lines of reasoning support the possibility. First, the mathematics of general relativity and quantum field theory suggest that the extreme conditions within black holes could indeed lead to the emergence of new spacetime regions with their own independent evolution. This mathematical consistency does not prove the theory, but establishes it as a possibility within our best physical frameworks. Second, the striking similarities between black hole interiors and early universe conditions invite explanation. Both involve singularities, where current physics breaks down, both include regions of incredible density and curvature, and both create causal boundaries that prevent information flow between regions. These parallels might be coincidental, but they might also indicate a deeper connection. Third, the black hole universe theory resolves several persistent puzzles in cosmology, including the origin of cosmic inflation, the extreme flatness and homogeneity of our universe, and the apparent fine-tuning of physical constants for structure formation. While other explanations exist for each of these puzzles individually, the black hole connection offers a unified framework addressing multiple issues simultaneously. Let us explore what this connection would mean for our understanding of cosmic history. If our universe exists inside a black hole in a parent cosmos, that parent itself might exist inside a black hole in a grandparent universe, and so on, potentially without end. Reality would be structured like a vast fractal, with universes nested within black holes nested within universes, each level similar in pattern, but unique in specific details. From our perspective within our universe, we cannot directly observe these other cosmic levels. The boundary of our observable reality would be the event horizon of the black hole containing us, appearing to us not as a location in space, but as the earliest moment of cosmic time, what we call the Big Bang. Beyond this boundary, we cannot see or interact, just as nothing inside a conventional black hole can communicate with the external universe. Yet the structure of our cosmos might bear the imprint of this nested relationship. Some cosmologists have suggested that certain large-scale patterns in the cosmic microwave background The afterglow of the Big Bang might contain subtle signatures of our universe's birth from a black hole. These could include particular types of asymmetry or correlation that would be difficult to explain in a universe that emerged spontaneously from nothing. The total mass energy of our universe would equal the mass energy of everything that fell into the parent black hole. This correspondence would maintain conservation principles across the cosmic boundary, with nothing created or destroyed, but only transformed from one context to another. The physical constants of our universe, like the strength of gravity or the mass of the electron, might represent slightly modified versions of the constants in the parent cosmos, variations introduced during the birth process. The concept of cosmic time takes on new meaning in this framework. What we perceive as the beginning of time, the Big Bang about 14 billion years ago, would connect to a particular moment in the parent universe's timeline when matter collapsed into the black hole that birthed our cosmos. Our entire universal history, from Big Bang to the present and beyond, would be contained within what the parent universe would perceive as a black hole at a specific location and time. This temporal relationship creates a curious asymmetry. We cannot access the history of the parent universe before our cosmic birth, but any intelligent life in that cosmos could potentially know about us, at least in principle, by studying the black hole that contains our universe. They would perceive our entire cosmic history as encoded in the properties of that black hole, though practical limitations would prevent them from extracting detailed information about our existence. The concept of our universe as a black hole interior also transforms our understanding of cosmic expansion. In conventional cosmology, the universe expands because that's its initial condition, set at the Big Bang for reasons we don't fully understand. In the black hole universe model, this expansion has a more concrete explanation. It represents the time-reversed view of matter collapsing into a black hole in the parent cosmos. What appears as universal expansion from our perspective would be cosmic collapse viewed from the other side. This perspective might also shed light on dark energy, the mysterious force accelerating our universe's expansion. Some theoretical models suggest that the repulsive torsion generated in Einstein-Cartan theory, which would drive the initial bounce of a black hole universe, might persist as a subtle effect, gradually accelerating cosmic expansion over billions of years. Dark energy would not be an ad hoc addition to explain observations, but an intrinsic feature of a universe born from a black hole. The temperature and density profile of our early universe matches what we would expect from the interior of a bouncing black hole. The initial ultra-hot, ultra-dense state cools as it expands, eventually allowing matter to condense into structures. This cooling expansion mirrors, in reverse, the heating compression of matter falling into a black hole in the parent universe. The quantum fluctuations that seeded cosmic structure formation, the slight variations in density that eventually grew into galaxies and galaxy clusters, might originate from quantum processes during the bounce event. The specific pattern of these fluctuations, which we observe in the cosmic microwave background, might contain encoded information about the black hole that birthed our universe. As we examine our cosmic beginning through this lens, familiar features take on new significance. The horizon problem in cosmology asks why distant regions of our universe, which should never have been in causal contact, nevertheless have the same temperature and density. Cosmic inflation provides one explanation, but the black hole universe offers another. If our cosmos emerged from a single collapsed object in a parent universe, its uniformity would be natural rather than puzzling. Similarly, the flatness problem, the observation that space has almost exactly zero curvature on the largest scales, finds a natural explanation. The interior of a large black hole would create a space-time that appears nearly flat to observers within it, just as the surface of the Earth seems flat to us despite its global curvature. What requires fine-tuning in standard cosmology emerges naturally from the black hole universe perspective. Even the matter composition of our universe, with its precise ratios of dark matter, normal matter and radiation, might reflect the specific properties of the parent black hole. The proportions of different types of matter and energy would be determined by what fell into that black hole and how it was processed during the bounce event. This framework transforms how we view our cosmic origin. Rather than emerging spontaneously from nothing, our universe would have a concrete cause, the collapse of matter in another cosmos. The Big Bang would not be an absolute beginning, but a transition. a birth event connecting our reality to a parent universe, takes on a different character when something has always existed, cycling through different cosmic manifestations. Yet this perspective also introduces new questions. If our universe was born from a black hole, what caused the black hole? What is the nature of the parent universe? Does the chain of cosmic ancestry extend infinitely into the past, or was there an original universe that began the process of cosmic reproduction? These questions may lie beyond our ability to answer observationally, but they highlight how the black hole universe theory shifts the boundaries of cosmological inquiry. The black hole universe concept resonates with certain philosophical and religious traditions that envision reality as cyclical rather than linear. Many ancient cosmologies, from Hindu to Norse to certain Native American traditions, describe worlds emerging from the remains of previous worlds in an eternal cycle of creation and transformation. Modern physics, through the black hole universe theory, offers a mathematical framework that captures similar intuitions about cosmic renewal. For observers like ourselves, contemplating this possibility induces a strange blend of humility and wonder. Our entire cosmos, with its billions of galaxies extending billions of light years in all directions, might be contained within what another universe perceives as a single black hole. Yet this containment doesn't diminish the richness of our reality or the significance of our experiences within it. Each universe in the cosmic family tree would be a complete reality from within, regardless of its relationship to other cosmic domains. The question of whether we could ever confirm this theory empirically remains open. Direct observation beyond our cosmic boundary is impossible by definition, as information cannot escape the event horizon of the black hole containing our universe. But indirect evidence might accumulate through advances in theoretical physics, astronomical observations of our early universe, and perhaps even experimental insights into the behavior of space-time under extreme conditions. The theoretical physicist Bernard Carr has proposed that certain features of our universe, like the specific spectrum of density fluctuations in the cosmic microwave background, might bear the imprint of a black hole birth. These signatures would be subtle, but potentially distinguishable from the predictions of other cosmological models. As our observational tools and theoretical understanding advance, we might find increasing evidence supporting or challenging the black hole universe hypothesis. For now, this perspective offers a conceptual framework that connects black holes and cosmic birth, suggesting that the apparent beginning of our universe might be more accurately viewed as a transition within a larger cosmic context. If this view is correct, then we have always been inside a black hole. Our entire cosmic history has unfolded within what another universe would perceive as a region of space from which nothing can escape. The darkness that we imagine at the center of black holes in our universe might be filled with the light of new cosmos, just as our universe shines with the light of billions of galaxies, despite being contained within what another reality perceives as a black hole. The boundary as the beginning, the horizon as the origin, the apparent birth of everything from nothing, revealed as the transition from one cosmic context to another. These perspectives transform our understanding of both black holes and the Big Bang, suggesting that what we perceive as the most destructive and creative forces in nature might be two sides of the same cosmic process, a continual transformation of reality across the boundaries of universes. As we drift further into the cosmic possibilities of black holes, let us now explore their role as containers of matter and information, vessels that might harbor the seeds of new creation. If black holes can indeed generate new universes, they function not merely as cosmic endpoints, but as cosmic incubators, preserving the essence of collapsed matter and transforming it into new realities. A seed contains all the genetic information needed to grow a complex organism, compressed into a tiny, durable package. It waits in dormancy until conditions allow for germination, whereupon it unfolds into something vastly larger and more intricate than itself. Black holes may serve a similar function in the cosmic ecosystem, containing the compressed essence of collapsed stars and galaxies, waiting for the appropriate transition to unfold into new universes. To understand black holes as cosmic seeds, we must first explore how they store and process information. When matter falls into a black hole, its structure seems to be erased from our perspective. A star with its intricate fusion layers, a planet with its complex geology, even a living organism with its remarkable biological organization, all appear to be reduced to just three numbers as they cross the event horizon: the black hole's mass, electric charge, and angular momentum. This apparent simplification is known as the no-hair theorem, suggesting that black holes have no distinguishing features beyond these basic properties. Yet quantum physics complicates this picture. According to quantum mechanics, information cannot be truly destroyed. The quantum state of particles entering a black hole must be preserved in some form, even if transformed beyond recognition. This tension between general relativity, which suggests information loss, and quantum mechanics, which forbids it, creates the infamous black hole information paradox, a puzzle that has challenged physicists for decades. One resolution to this paradox suggests that information falling into a black hole becomes encoded on its event horizon rather than disappearing into the singularity. The horizon would function as a kind of cosmic hard drive, storing the complete quantum state of everything that fell in. This perspective, inspired by the holographic principle, transforms our understanding of black holes from simple gravitational traps to complex information processing systems. If information is indeed preserved on the event horizon, black holes become cosmic seed banks, storing in compressed form the complete quantum description of everything they have consumed. This encoded information might serve as the template or genetic code for a new universe, determining its fundamental parameters and initial conditions. As a black hole evaporates through Hawking radiation, this stored information faces an uncertain fate. Stephen Hawking initially believed the radiation would be purely thermal, carrying no information about what fell in, effectively destroying information and violating quantum principles. Later, he revised this view, suggesting that subtle correlations in the radiation might preserve information after all, allowing it to escape the black hole gradually as it evaporates. But there is another possibility. Rather than escaping back into the parent universe through Hawking radiation, the information stored in a black hole might flow forward into a baby universe. The compressed matter and encoded information would serve as the seed for a new cosmic reality, preserving the essential patterns of the parent universe while allowing for variations and new possibilities. This seeding process might occur at a specific moment in a black hole's life cycle. Some theoretical frameworks suggest that when a black hole reaches a critical threshold, either of minimum or maximum size depending on the model, it might undergo a phase transition that channels its stored energy and information into the creation of a new space-time region. For stellar mass black holes, this transition might occur only after trillions of years of evaporation, when the black hole has shrunk to microscopic size and approaches the realm where quantum gravitational effects dominate. For supermassive black holes, the transition might happen through a different mechanism, perhaps involving the extreme curvature of space-time at the central singularity without requiring significant evaporation. Regardless of the specific trigger, the moment of universe birth would represent a fundamental transformation, a cosmic phase transition, where the concentrated essence of a black hole unfolds into an entirely new dimensional framework. Like a seed splitting its coat as the embryonic plant emerges, the black hole would channel its stored potential into a new creation. The analogy to biological seeds extends further when we consider the role of dormancy. A seed can remain viable for years, decades, or sometimes centuries, waiting for the right conditions to germinate. Similarly, a black hole might contain the potential for universal creation in a dormant state, preserving its stored information and energy until the appropriate transition point is reached. This perspective transforms how we view the eventual fate of our universe. In the standard cosmological model, our cosmos faces a bleak future of eternal expansion, with galaxies moving ever further apart, stars gradually burning out, and matter either dispersing into the void or collapsing into black holes. Eventually, even these black holes would evaporate through Hawking radiation, leaving a cold, empty cosmos. But if black holes are cosmic seeds, this apparent end becomes merely a transition. The black holes formed during our universe's lifetime would each carry forward a portion of our cosmic legacy, preserving patterns of information and energy that would unfold in new universal contexts. Our universe would not truly die, but would live on through its cosmic offspring, like a plant completing its life cycle by producing seeds for the next generation. The theoretical physicist Lee Smolin has extended this concept into what he calls cosmological natural selection. In this framework, each black hole creates a new universe with slightly modified physical parameters. Over many generations of cosmic reproduction, universes particularly effective at producing black holes would dominate the cosmic population. Our universe, with its abundant galaxies harboring supermassive black holes at their centers, appears well adapted for prolific cosmic reproduction. This evolutionary perspective suggests that physical constants might be passed down with modifications across cosmic generations, like genetic traits in biological reproduction. Small variations in parameters, like the strength of gravity, the mass of elementary particles, or the cosmological constant, would create diversity in the cosmic family tree, allowing for the exploration of different physical possibilities over many universal generations. Some of these variant universes would be cosmic dead ends, with physical laws that don't allow for complex structures or abundant black holes. Others would be even more fertile than our own, producing black holes and thus baby universes at a greater rate. Over time, the multiverse would become dominated by universes particularly good at cosmic reproduction. Intriguingly, many of the same conditions that favor black hole formation also create environments where complexity and potentially life can emerge. Stable stars, necessary for black hole formation through supernovae, also provide the steady energy sources that might nurture living systems. The nuclear reactions that forge heavy elements eventually forming black holes also create the chemical diversity needed for complex structures like planets and potentially organisms. This correlation suggests that universes selected for black hole abundance might incidentally create conditions favorable for life and intelligence. We might exist not by cosmic coincidence or design, but as a side effect of selection pressures favoring universes that efficiently create cosmic seeds. For conscious beings contemplating this possibility, black holes transform from fearsome cosmic destroyers to vessels of creative potential. The matter falling into a black hole would not face final obliteration, but transformation and rebirth. Its patterns and structures, though altered beyond recognition, would contribute to new cosmic possibilities, new arrangements of reality, new potential for complexity and consciousness. This perspective invites us to reconsider the nature of cosmic death and rebirth. When a star explodes as a supernova, we don't typically view it as an absolute end, but as a transformation. Its matter scattered to form new stars and planets. Similarly, the apparent death represented by a black hole might be better understood as a metamorphosis, a change of state that preserves essence while transforming form. The information contained in matter falling into a black hole would undergo a similar transformation. The specific arrangements and relationships embodied in complex structures would be encoded, preserved, and eventually expressed in new forms in the baby universe. Not exactly the same, just as a child is not identical to its parent, but carrying forward essential patterns and possibilities. Some theoretical frameworks suggest that entanglement across the event horizon plays a crucial role in preserving information. Similarly, quantum entanglement might create connections between a parent universe and its offspring, subtle correlations that preserve patterns across cosmic generations. These quantum threads would not allow for causal influence or communication between universes, but would maintain the coherence of reality across the boundaries between cosmic domains. As a black hole shrinks through Hawking radiation, its temperature increases and its evaporation accelerates. A stellar mass black hole would take unimaginable times to evaporate, roughly 10 to the 67 years, far longer than the current age of the universe. But eventually, it would reach a critical point where quantum gravitational effects dominate its behavior. At this final stage, theoretical models diverge. Some suggest the black hole would evaporate completely in a final burst of energy. Others propose that a stable remnant might remain, a microscopic quantum object containing all the information of the original black hole. And some suggest this moment might trigger the birth of a baby universe, channeling the black hole's remaining energy and encoded information into a new cosmic domain. This final possibility transforms the death of a black hole from an ending to a beginning. The final moments of evaporation, rather than representing the erasure of everything that fell in, would mark the germination of a cosmic seed, the emergence of new space, time, and possibility from the concentrated essence of collapsed matter. This perspective gives new meaning to the life cycle of stars. A main sequence star like our Sun shines by fusing hydrogen into helium, maintaining a delicate balance between gravitational collapse and the outward pressure of nuclear fusion. When this balance eventually shifts, the star may explode as a supernova if massive enough, leaving behind a neutron star or black hole. This stellar death, once seen as the end of a cosmic story, becomes merely a transition between chapters if the resulting black hole eventually seeds a new universe. The matter and energy from countless stars might contribute to a single black hole, which in turn generates a baby universe. That new cosmos might develop its own stars, planets, and potentially life, continuing the cycle of cosmic creativity across universal generations. The hydrogen atoms in your body, forged in the Big Bang and cycled through generations of stars, might one day form part of a black hole that births an entirely new universe. This cycling of matter and information creates a profound continuity across cosmic domains. Nothing is truly lost, merely transformed and channeled into new expressions of reality. The collapse that seems like an ending from one perspective becomes a creation when viewed from another angle, like a supernova that seems destructive up close but generative when we recognize how its scattered elements seed new cosmic structures. Black holes might vary in their effectiveness as cosmic seeds depending on their properties. Supermassive black holes at galactic centers, containing the mass of millions or billions of suns, might generate particularly large and energetic baby universes. Rotating black holes, with their more complex internal geometry, might create offspring with different properties than non-rotating black holes. Charged black holes might imprint their electromagnetic properties on their universal progeny in unique ways. This diversity of cosmic seeds would contribute to the diversity of the multiverse, creating a rich tapestry of realities, each with its own distinct character derived from its parent black hole. Some baby universes might inherit subtle imprints of specific structures from our cosmos, carrying forward patterns that would influence their own evolution and development. The concept of black holes as cosmic seeds resonates with ancient intuitions about cycles of death and rebirth. Many cultural traditions envision reality as a continuous process of renewal, rather than a linear progression with absolute beginnings and endings. Modern physics, through the black hole universe theory, offers a mathematical framework that captures similar insights about the transformative, rather than destructive nature of apparent endings. For conscious observers contemplating this possibility, black holes transform from cosmic dead ends to cosmic wombs, places where reality continues in new forms beyond our direct perception. The matter falling into a black hole, including potentially conscious beings, would not face final obliteration but transformation, its patterns preserved and expressed anew in a different cosmic context. This preservation would not constitute personal immortality in any conventional sense. An individual falling into a black hole would not maintain their specific consciousness or identity in the baby universe. But the information patterns that constituted their existence would contribute to the initial conditions of the new cosmos, perhaps influencing its development in subtle ways beyond our current understanding. From every ending, a question remains. From every black hole, a possibility. As these cosmic seeds drift through the darkness of our universe, they may be quietly nurturing new realities within, waiting for the moment when what seems like death from our perspective blossoms into birth from another. Like seeds scattered across cosmic soil, each black hole might contain within it the potential for an entire universe, for galaxies and stars, planets, and perhaps even life, waiting to unfold when conditions allow for cosmic germination. One of the most profound puzzles in modern physics centers around what happens to information when it falls into a black hole. This question, known as the black hole information paradox, has challenged our understanding of reality for nearly half a century. Yet within this seemingly technical conundrum may lie profound insights into the possibility of universe creation through black holes. The paradox emerged in the 1970s when Stephen Hawking made the revolutionary discovery that black holes are not entirely black. Due to quantum effects near the event horizon, they emit a faint radiation and slowly evaporate over time. This Hawking radiation appeared to be purely thermal, carrying no information about what fell into the black hole. This created a direct conflict with a fundamental principle of quantum mechanics, that information cannot be destroyed. When matter falls into a black hole, it carries with it all its complexity and structure, all the specific arrangements of its particles and fields, all the information that makes it uniquely what it is. According to quantum mechanics, this information must be preserved even as the physical form changes. Yet Hawking's calculations suggested that as a black hole evaporates completely, this information would be permanently lost, violating a core principle of our most successful physical theory. The implications were severe. Either quantum mechanics was incomplete, or our understanding of black holes was flawed, or some deeper principle reconciled these apparently contradictory perspectives. The paradox forced physicists to confront fundamental questions about the nature of information, causality, and reality itself. Over the decades, various resolutions to this paradox have been proposed. Hawking himself eventually changed his position, suggesting that subtle correlations in the radiation might preserve information after all, allowing it to escape gradually as the black hole evaporates. Others proposed that information might be stored in a stable remnant that remains after evaporation, or that it might be preserved in extra dimensions beyond our direct perception. But among the most intriguing possibilities is that information falling into a black hole isn't lost at all, but passed into a new universe. If black holes can generate baby universes, as we've explored in previous chapters, then the information that seems to vanish from our perspective might simply be transitioning to a new cosmic context. Black holes would function not as information destroyers, but as information bridges, channels through which the patterns and structures of our universe flow into new realities. This perspective transforms the information paradox from a troubling inconsistency into a window onto a larger cosmic process. Information isn't destroyed when it falls into a black hole, but neither does it return to our universe through Hawking radiation. Instead, it flows forward into a baby universe, preserved but transformed, like genetic information passed from parent to child. To understand how this might work, we need to explore the nature of information itself. In physics, information isn't just data in the conventional sense, but the complete specification of a physical system, the precise state of all its particles and fields. This quantum information describes not just the obvious properties like position and momentum, but all the subtle correlations and entanglements that define a system's entire state. When matter falls into a black hole, its quantum information would be preserved even as its physical form is transformed beyond recognition. The specific pattern of a star, a planet, or even a living organism would be encoded in a new form, perhaps as quantum fluctuations in the seed of a baby universe, or as subtle correlations in the fabric of new spacetime. This preservation would maintain what physicists call quantum coherence, the delicate relationships between particles that allow quantum systems to exist in multiple states simultaneously. The coherence of the original matter would be transferred to the new universe, maintaining the fundamental integrity of reality across the cosmic transition. The mechanism for this information transfer remains speculative, but several frameworks offer potential pathways. One possibility involves quantum entanglement across the event horizon. Another approach draws on the holographic principle, which suggests that all the information contained in a volume of space can be encoded on its boundary. Applied to black holes, this principle indicates that information falling in gets encoded on the event horizon rather than reaching the singularity. This encoded information might serve as the template for the new universe, projecting its patterns into the emerging cosmic domain. Some theoretical models suggest that information might be transferred through a kind of tunneling process, where the quantum state of collapsing matter transitions directly into the initial state of a baby universe. The information wouldn't be destroyed or even substantially altered, just relocated to a new dimensional framework where it would influence the evolution of the new cosmos. This information transfer would not be random or chaotic, but structured according to the physical laws governing black holes and quantum fields. The specific properties of the parent black hole, its mass, charge, and angular momentum, would shape how information flows into the baby universe, creating correlations between the characteristics of the black hole and the fundamental parameters of its cosmic offspring. The preservation of information across universe boundaries resolves the paradox that troubled Hawking and others. Information doesn't disappear when it falls into a black hole, nor does it need to escape back into the parent universe through some complex mechanism. It simply continues its journey in a new context, maintaining the coherence of reality across cosmic generations. This resolution has profound implications beyond the technical details of quantum mechanics. It suggests a kind of cosmic memory, where the patterns and structures of our universe influence the development of future cosmos, creating a continuity of information across seemingly unbridgeable boundaries. Consider a star falling into a supermassive black hole. From our perspective, it would be stretched, compressed, and eventually reduced to its basic constituents as it crossed the event horizon, its distinctive structure apparently lost. But in the black hole universe framework, the specific pattern of that star, the precise quantum state of all its particles and fields, would help shape the initial conditions of a baby universe. The star wouldn't be reborn in recognizable form, but its information would contribute to the cosmic DNA of the new universe, subtly influencing its development, just as genetic information shapes, but doesn't completely determine the growth of a living organism. This transfer would preserve the underlying coherence of reality while allowing for new expressions and possibilities. This perspective transforms our understanding of black holes from cosmic dead ends to cosmic bridges, connecting one universe to another through the flow of information. What appears as destruction from one side becomes creation when viewed from the other, with information serving as the thread that maintains continuity across this profound transition. In the black hole universe framework, the apparent destruction of matter falling into a black hole becomes the creation of a new cosmic domain, with information serving as the conserved quantity that balances the cosmic equation. This balance addresses one of the persistent puzzles in cosmology, the origin of the low entropy state at the beginning of our universe. Entropy, a measure of disorder or randomness, tends to increase over time in isolated systems, yet our universe began in a state of remarkably low entropy, a highly ordered configuration that has allowed for the subsequent emergence of structure and complexity. If our universe was born from a black hole in another cosmos, its low initial entropy might be explained by the specific way information transfers across the cosmic boundary. This transfer would not be perfectly efficient. Some information might be scrambled or modified during the transition, creating variations between parent and child universes. These variations would allow for cosmic evolution, with each generation of universes exploring slightly different configurations of physical law and initial conditions. Over many generations, this process would create a diverse multiverse of realities, each with its unique informational signature derived from, but not identical to, its ancestors. Some of these variations would lead to universes particularly effective at producing their own black holes, and thus their own cosmic offspring, creating a kind of natural selection among informational patterns across cosmic domains. The black hole information paradox, once seen as a troubling inconsistency in our physical theories, becomes in this framework a window onto a greater cosmic process, the flow of information across universe boundaries that maintains the coherence of reality on the largest scales. Black holes are not where information goes to die, but where it transforms and continues, bridges rather than endpoints in the cosmic story. This continuity suggests a kind of cosmic conservation principle, where information is neither created nor destroyed, but only transformed as it flows through black holes into new universal contexts. The total information content of the multiverse would remain constant, even as it takes different forms in different cosmic domains. For conscious observers contemplating this possibility, black holes transform from fearsome destroyers to cosmic connectors, places where the patterns and structures of our universe continue their journey in new forms beyond our direct perception. The information that constitutes our existence, the precise quantum state of the particles that make up our bodies and minds, might one day contribute to the initial conditions of a new cosmos if it falls into a black hole. This would not constitute personal immortality in any conventional sense. An observer falling into a black hole would not maintain their specific consciousness or identity in the baby universe, but the information patterns that constituted their existence would flow forward into the new cosmic domain, perhaps influencing its development in subtle ways beyond our current understanding. The black hole information paradox connects to deeper questions about the nature of reality itself. If information is truly fundamental, as many physicists now believe, then its preservation across cosmic boundaries maintains the underlying coherence of existence, even as its expressions change. Nothing is truly lost, merely transformed and channeled into new forms as reality cycles through its cosmic generations. This perspective resonates with ancient philosophical intuitions about the conservation of essence amid the transformation of form. Many traditional worldviews envision reality as a continuous process of renewal rather than a linear progression with absolute creations and destructions. Modern physics, through the black hole information theory, offers a mathematical framework that captures similar insights about the fundamental continuity of existence. The flow of information across universe boundaries also addresses a profound question in cosmology: whether the patterns and structures of our universe are purely random or, in some sense, inherited from a deeper reality. If our cosmos was born from a black hole in another universe, its specific characteristics would not be random, but derived from the information that flowed through that black hole during our cosmic birth. This inheritance would not be a simple copying process, but a complex transformation, with information being reconfigured as it transitions from one cosmic domain to another. The specific laws of physics in our universe, the values of fundamental constants, the distribution of matter and energy in the earliest moments, might all bear the imprint of the parent universe, modified through the lens of the black hole that connected them. Some theoretical frameworks suggest that this inheritance might be observable, at least in principle. Certain patterns in the cosmic microwave background, the afterglow of the Big Bang, might contain subtle signatures of our universe's birth from a black hole. These could include specific types of asymmetry or correlation that would be difficult to explain in a universe that emerged spontaneously from nothing. The information flow through black holes also offers a new perspective on the future of our universe. In conventional cosmology, our cosmos faces a bleak fate of eternal expansion and eventual heat death, with all structure gradually dissolving into uniform, cold emptiness. But if black holes channel information into new universes, this apparent end becomes merely a transition in the larger cosmic story. The black holes formed during our universe's lifetime would each carry forward a portion of our cosmic information, preserving patterns and structures that would influence new universal domains. Our universe would not truly end, but would live on through its informational legacy, encoded in the baby universes born from its black holes. This continuity transforms how we might view cosmic purpose. Rather than being temporary structures in a universe inexorably moving toward thermal equilibrium and emptiness, we might be participants in an eternal process of information processing and transfer across cosmic generations. The patterns we create during our existence might contribute in some small way to the informational inheritance of future universes. The black hole information theory suggests a profound revision of our cosmic narrative. Instead of a universe that began from nothing and will end in empty silence, we glimpse an eternal cycling of information through black holes into new cosmic expressions, a continual transformation rather than creation and destruction. Nothing is truly lost, not even when it falls into the darkest regions of our cosmos. Even the darkest places may carry every story ever told. The information that seems to vanish into a black hole's abyss continues its journey beyond our perception, flowing into new cosmic domains where it takes new forms and contributes to new possibilities. Black holes become not the end of information, but its transit points, portals through which the patterns of our universe pass into new realities. In this view, the universe becomes not just a physical system, but an informational one, a vast process of pattern creation, transformation, and transmission across cosmic boundaries. Black holes serve as the crucial nexus in this process, the channels through which information flows from one universe to another, maintaining the coherence of reality across the generations of cosmic existence. As we've journeyed through the theoretical landscape of black holes as universe generators, we arrive at a crucial question. Could we ever know if these extraordinary possibilities are true? Could science eventually confirm or refute the idea that black holes create new universes? Or will this concept remain perpetually in the realm of fascinating but untestable speculation? The challenge is profound. By definition, the interior of a black hole beyond the event horizon is causally disconnected from our universe. Nothing, not even light, can escape to bring us information about what happens inside. Furthermore, if black holes do indeed create new universes, these cosmic offspring would exist in separate space-time domains, inaccessible from our own, except through the one-way passage of the black hole itself. This observational barrier seems absolute. We cannot peer beyond the event horizon, much less glimpse a baby universe that might be growing within. We cannot send probes into a black hole and retrieve data, as anything crossing the horizon can never return. We cannot receive signals from a child universe, as information cannot flow backward through the black hole that connects us. Yet despite these fundamental limitations, science often finds indirect ways to test seemingly untestable ideas. The atomic theory of matter was once considered philosophically interesting, but possibly beyond empirical verification. Today, we can not only confirm the existence of atoms, but image them directly. Similarly, while we may never observe a baby universe directly, other avenues of investigation might eventually provide compelling evidence for or against the black hole creation hypothesis. One approach involves developing the theoretical framework to its fullest extent and checking for mathematical consistency. If black holes do create new universes, this process must conform to the established principles of physics, particularly the conservation of energy, momentum, and information. Theoretical physicists can explore whether a mathematically coherent model can be constructed where these conservation laws are maintained across universe boundaries. Current work in quantum gravity, string theory, and loop quantum cosmology is already addressing these questions, examining whether the physics of black hole interiors naturally leads to the birth of new space-time regions. If these theoretical investigations reveal fundamental inconsistencies or contradictions, they might rule out the black hole universe scenario. Conversely, if they demonstrate the mathematical coherence and physical plausibility of the process, they would strengthen the case for taking these ideas seriously. Another avenue involves searching for indirect observational signatures that might be accessible within our universe. While we cannot see beyond the event horizon of a black hole, the physics governing universe creation would also influence the observable properties of the black hole itself, potentially leaving detectable imprints. For instance, the process of universe creation might affect how a black hole evolves, its mass, charge, or spin changing in subtle but potentially measurable ways. If new universes are born from black holes, the parent black hole in our universe might exhibit specific behaviors that differ from black holes that do not generate offspring. Precise observations of black hole properties, particularly during merger events detected through gravitational waves, might eventually reveal patterns consistent with universe creation. Physicists can explore this prediction by modeling how black hole production would change if parameters like the strength of gravity, the mass of elementary particles, or the cosmological constant were slightly different. If most small variations indeed reduce black hole abundance, this would be consistent with the cosmic natural selection hypothesis. If many variations would increase black hole production, it would suggest our universe is not optimized, as the theory predicts. Another potential source of evidence might come from the cosmological domain. If our universe was born from a black hole in another cosmos, its initial conditions and large-scale properties might bear the imprint of this origin. Detailed observations of the cosmic microwave background, the afterglow of the Big Bang, might reveal patterns or asymmetries that would be difficult to explain in a universe that emerged spontaneously from nothing but consistent with a black hole birth. Some theoretical models suggest that the specific spectrum of density fluctuations in the early universe, which eventually grew into the galaxies and galaxy clusters we observe today, might contain subtle signatures of a black hole origin. As our observational tools and data analysis techniques become increasingly sophisticated, we might detect such signatures, providing indirect evidence for our cosmic parentage. Advanced civilizations, if they exist elsewhere in our universe or will exist in the future, might develop even more sophisticated approaches to testing these ideas. While the direct observation of baby universes might remain forever beyond reach, theoretical frameworks and observational techniques unimaginable to us now might eventually provide compelling evidence regarding the fate of matter in black holes and the possibility of universe creation. Some speculative proposals suggest that extremely advanced civilizations might even attempt to influence the process directly. If black holes do create new universes, and if the properties of the parent black hole determine the characteristics of its cosmic offspring, then a sufficiently advanced civilization might theoretically create black holes with specific properties designed to generate universes particularly hospitable to complexity or life. This concept of artificial cosmos creation, sometimes called cosmological engineering, represents an extraordinary extension of technological capability beyond anything currently conceivable. Yet, if the underlying physics proves correct, it presents the possibility that some black holes might function as intentional seeds for new universes rather than merely natural processes. The creation of microscopic black holes in laboratory settings through extremely high-energy particle collisions has been proposed as theoretically possible, though far beyond current technological capabilities. If such creation becomes possible in the distant future, it might allow for controlled experiments related to black hole physics that could indirectly test theories of universe generation. Even without direct empirical verification, the black hole universe theory holds scientific value. It provides a coherent framework that potentially resolves multiple puzzles in contemporary physics, from the information paradox to the fine-tuning of physical constants. It connects previously separate domains of inquiry, suggesting links between quantum gravity, cosmology, and thermodynamics, and it generates new questions and research directions, stimulating theoretical work that advances our understanding regardless of whether the specific hypothesis proves correct. The history of science includes many examples of theories that were initially considered untestable, but eventually found empirical support through unexpected avenues. The expansion of the universe, the existence of subatomic particles, and the bending of light by gravity were all once theoretical predictions that seemed beyond observational reach. Yet creative experimental approaches eventually brought them into the realm of testable science. The philosopher of science Karl Popper suggested that the demarcation between science and non-science lies in falsifiability, the possibility of being proven wrong through observation or experiment. While direct observation of baby universes may be impossible, the theoretical framework makes other predictions that could potentially be falsified, maintaining its status as a scientific hypothesis rather than metaphysical speculation. Even if definitive proof remains elusive, the accumulation of indirect evidence and theoretical coherence might eventually lead to a scientific consensus regarding black hole universe creation, similar to how multiple lines of evidence support theories like cosmic inflation or the evolutionary origin of species, even though certain aspects remain difficult to test directly. There's also the possibility that advances in fundamental physics might reveal alternative ways of conceptualizing these questions. Just as Einstein's general relativity transformed our understanding of gravity from a force to a curvature of space-time, future theoretical frameworks might change how we think about black holes, universe creation, and the boundaries between cosmic domains. The development of a comprehensive theory of quantum gravity, unifying the physics of the very small with the physics of the very large, might provide new perspectives on what happens at the center of a black hole. Such a theory might reveal whether the mathematical singularity predicted by general relativity is replaced by a bounce, a tunnel, or some other process that could lead to universe creation. String theory, loop quantum gravity, causal set theory, and other approaches to quantum gravity each offer different perspectives on black hole interiors and the possibility of universe generation. As these frameworks advance and potentially converge, they might provide increasingly robust theoretical foundations for evaluating the black hole universe hypothesis. Computational approaches might also contribute to our understanding. While we cannot directly simulate the interior of a black hole or the birth of a universe with current computing technology, advances in quantum computing and numerical relativity might eventually allow for sophisticated simulations that capture relevant aspects of these extreme processes, providing insights into their theoretical possibility. Philosophical analysis can likewise play a role in evaluating these ideas. The black hole universe theory has implications for concepts like causality, determinism, the nature of time, and the meaning of creation. Philosophical investigation of these implications can help clarify the conceptual coherence of the theory and its relationship to other frameworks for understanding reality. For now, the question of whether black holes create new universes remains open, with compelling theoretical arguments supporting the possibility, but direct empirical confirmation remaining beyond our reach. The question hovers at the boundary between established science and theoretical exploration, between what we can know and what we might only infer from mathematical consistency and indirect evidence. This boundary status does not diminish the significance of the question. Throughout history, some of the most profound advances in our understanding have come from exploring ideas that initially seemed to transcend our observational capabilities. From atoms to quarks, from the Big Bang to dark energy, concepts that once appeared metaphysical have gradually entered the domain of empirical science through theoretical development and observational ingenuity. The black hole universe theory might follow a similar trajectory, moving from speculative hypothesis to established science through accumulating indirect evidence and theoretical refinement. Or it might remain permanently in the realm of compelling but unverifiable possibilities, a reminder of the limits of human knowledge when confronting the most extreme domains of physical reality. Either outcome has value for our understanding. If the theory proves correct, it would transform our cosmic perspective, revealing our universe as one branch in a vast family tree of realities connected through black holes. If it proves incorrect or permanently untestable, the exploration itself advances our theoretical frameworks and clarifies the boundaries of scientific inquiry. For those who feel philosophical discomfort with ideas that might lie beyond empirical verification, it's worth noting that many concepts now central to our scientific worldview once occupied similar territory. The atomic theory was considered by some philosophers to be an untestable metaphysical position until observational techniques advanced sufficiently. Continental drift was rejected partly because no mechanism seemed capable of moving entire continents until plate tectonics provided the explanation. The history of science encourages both optimism about our ability to test seemingly untestable ideas and humility about the potential limitations of knowledge. It reminds us that the boundary between the observable and the unobservable, between science and speculation, shifts as our theoretical understanding and observational capabilities advance. The question of black hole universe creation exemplifies this dynamic boundary. It connects the known physics of black holes, gravity, quantum mechanics, and thermodynamics to domains beyond our direct observation, challenging us to extend our understanding while respecting the constraints of empirical science. For conscious observers contemplating these possibilities, black holes transform from objects of fear or fascination to windows onto the deepest questions about cosmic origin, purpose, and continuity. Even if we can never see beyond the event horizon to confirm whether new universes bloom within, the exploration itself expands our intellectual horizons and reminds us of the vastness of potential reality beyond our direct perception. The silence that surrounds black holes, the absence of signals from beyond their boundaries, need not be interpreted as emptiness or finality. It might instead be pregnant with possibility, a silence that contains not the void, but the whispers of creation we cannot yet hear, the birth cries of universes we cannot yet see. We may never see beyond, but the silence is filled with hints. The mathematics of our best physical theories points toward possibilities beyond the horizon. The consistency of conservation principles suggests processes that preserve information and energy across cosmic boundaries. The apparent fine-tuning of our universe hints at a selective process that might operate through black hole reproduction. These hints do not constitute proof, but they invite continued exploration, both theoretical and observational. They remind us that the limits of our knowledge are not fixed, but expanding, that questions once considered beyond science might gradually yield to patient investigation and creative inquiry. The black hole universe theory occupies that fertile borderland between established knowledge and creative speculation, between what we know and what we can imagine as possible given our current understanding of physical law. It represents science at its most expansive, reaching toward the boundaries of what can be conceptualized while remaining grounded in mathematical consistency and the principles of empirical investigation. Whether these extraordinary possibilities will ever move fully into the domain of confirmed science remains an open question. But the inquiry itself, the rigorous exploration of what might lie beyond the black hole's veil, already enriches our understanding and expands our cosmic perspective. It reminds us that reality might be vaster, stranger, and more interconnected than we can directly observe, and that the darkness we perceive might harbor lights beyond our seeing. Throughout cosmic history, black holes have played a far more significant role than simply swallowing matter and light. These extraordinary objects shape the very evolution of galaxies, regulate star formation, distribute heavy elements across space, and potentially create new universes. As we contemplate their cosmic legacy, we begin to see black holes not as monsters, but as essential architects of reality, entities that both destroy and create on the grandest scales imaginable. Let us first consider their influence within our observable universe. At the center of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole with a mass millions or billions of times that of our Sun. These cosmic giants are not merely passive occupants of galactic centers, but active participants in galactic evolution. Through their gravitational influence and the energy released by matter falling into them, they help regulate the formation of stars throughout their host galaxies. When a supermassive black hole actively consumes matter, it creates what astronomers call an active galactic nucleus, one of the most energetic phenomena in the universe. Jets of particles accelerated to near light speed erupt from the regions near the black hole's poles, extending for thousands or even millions of light years. These jets inject enormous amounts of energy into the surrounding galactic environment, heating gas and preventing it from cooling enough to collapse into new stars. This feedback process creates a self-regulating system. As a galaxy grows and more gas flows toward its center, the central black hole becomes more active, eventually releasing enough energy to suppress further star formation. This prevents galaxies from growing too large too quickly and helps explain the observed relationship between the mass of a supermassive black hole and the size of its host galaxy's central bulge. Black holes also contribute to the chemical enrichment of the cosmos. When massive stars explode as supernovae before collapsing into stellar mass black holes, they scatter newly forged heavy elements across space. These elements, like carbon, oxygen, and iron, become the building blocks for new generations of stars, planets, and eventually life. The black holes left behind after these explosions continue to influence their surroundings through gravitational interactions, sometimes forming binary systems with stars or other black holes. When two black holes merge, they create some of the most powerful events in the universe. These mergers generate gravitational waves, ripples in the fabric of space-time that carry energy across cosmic distances. The detection of these waves by observatories like LIGO and Virgo has opened a new window onto the universe, allowing us to observe black hole mergers that emit no light but nonetheless shake the cosmic foundations. These contributions to cosmic evolution showcase black holes not as isolated anomalies, but as integral parts of the universal machinery. They regulate, distribute, and transform, participating in the grand cycles of matter and energy that shape our observable cosmos. But their legacy might extend far beyond what we can directly observe. If black holes do indeed create new universes, as we've explored throughout our journey, then their cosmic role expands dramatically. They would not merely shape galaxies, but birth entire realities, each with its own space, time, and evolutionary path. Black holes would serve as bridges between cosmic generations, channels through which matter and energy flow from one universal expression to another. In this expanded view, every black hole in our universe would be a point of cosmic creation, a seed from which a new universe might grow. The supermassive black holes at galactic centers would be particularly prolific cosmic parents, potentially generating universes with vast energy reserves derived from the enormous mass they contain. Stellar mass black holes would create smaller offspring, while primordial black holes formed in the extreme conditions of the early universe might have already generated countless baby cosmos throughout cosmic history. This creative role transforms our understanding of black holes from cosmic endpoints to cosmic beginnings, from destroyers to creators. The matter and energy that appear to be lost forever, when they fall into a black hole, would actually be repurposed. becoming the raw material for new cosmic expressions beyond our observational reach. This perspective resolves the apparent tension between creation and destruction in the cosmic process. Black holes embody both, serving as agents of transformation rather than absolute endings. They break down complex structures into simpler components, erasing specific patterns while preserving the essential energy and information needed to seed new possibilities. The parallel to biological processes is striking. In living systems, death and decomposition break down complex organisms into simpler molecules that become nutrients for new life. Nothing is wasted. Everything is transformed and reincorporated into the ongoing cycle of existence. Black holes might serve a similar function in the cosmic ecosystem, returning matter and energy to a primordial state from which new universal expressions can emerge. This cycling between complexity and simplicity, between structure and potential, creates a cosmic rhythm of dissolution and recreation across universe boundaries. Matter organizes into stars and galaxies over billions of years, some of it eventually falling into black holes where it is compressed toward a state of maximum density before expanding again in a new cosmic context. Each cycle would create opportunities for new forms and relationships to emerge, new possibilities for complexity and consciousness to develop. The black hole universe theory also transforms our understanding of cosmic purpose. In conventional cosmology, our universe appears to be winding down toward an eventual heat death, a state of maximum entropy where all energy is evenly distributed and no further work or complexity is possible. Black holes, as the ultimate entropy generators, seem to accelerate this cosmic decline. But if black holes create new universes, this apparent movement toward cosmic death becomes part of a larger process of cosmic renewal. Black holes would not be the final stage of cosmic evolution, but the transition point to new evolutionary cycles. The entropy they generate in our universe would become the raw potential for order and complexity in their universal offspring. This perspective resonates with ancient intuitions about cycles of creation and destruction, death and rebirth that appear in many cultural traditions. Modern physics, through the black hole universe theory, offers a mathematical framework that captures similar insights about the transformative rather than final nature of apparent endings. For conscious beings contemplating this possibility, black holes transform from fearsome cosmic monsters to essential participants in an eternal creative process. They remain objects of appropriate awe, given their extreme properties and enormous power, but this awe is tempered with appreciation for their potentially generative role in the larger cosmic story. The matter that constitutes our bodies, the carbon, oxygen, and other elements forged in stellar furnaces, might one day fall into a black hole and contribute to the formation of a new universe. Our physical substance would not be destroyed, but transformed and incorporated into new cosmic expressions, part of an endless cycle of matter and energy flowing through generations of universes. This material continuity extends to information as well. The specific patterns and relationships that constitute our existence, the precise quantum state of the particles that make up our bodies and minds, might influence the initial conditions of a baby universe if they fall into a black hole. Not as conscious beings with memories and identities, but as threads in the complex tapestry of information that flows from one cosmic expression to another. This flow of matter, energy, and information across universe boundaries creates a profound continuity underlying the apparent discontinuities of black holes. Nothing truly ends. Everything transforms. The darkness that seems to swallow light forever actually channels it into new expressions beyond our direct perception. The concept of black holes as cosmic midwives rather than cosmic graves fundamentally changes our relationship to these extraordinary objects. They remain the most extreme environments in our universe, places where the known laws of physics reach their limits and perhaps break down entirely. But they are not simply destroyers or cosmic waste bins. This reframing has philosophical as well as scientific implications. It suggests that apparent endings might always contain hidden beginnings, that destruction at one level might enable creation at another, that what seems like waste might actually be potential in disguise. These insights extend beyond cosmology to how we understand processes of transformation in many domains, from ecosystems to societies to personal development. The cosmic midwife metaphor also highlights the generative potential of extreme conditions. Black holes represent the most extreme environments possible in our universe, places where density, gravity, and space-time curvature reach their maximum values. Yet these extreme conditions might be precisely what enables the birth of new cosmic domains. The intensity that seems destructive from one perspective becomes creative when viewed from another angle or scale. Similarly, some of the most creative periods in human history have emerged from times of extreme challenge or transformation. The pressure that threatens to destroy can sometimes catalyze breakthrough and renewal. Black holes remind us that creation often emerges not from moderate, comfortable conditions, but from extremity, from boundaries where existing patterns break down and new possibilities can emerge. This creative potential extends across the different types of black holes that populate our universe. Stellar mass black holes, born from the collapsed cores of massive stars, might create universes with properties influenced by their stellar origins. Supermassive black holes at galactic centers, which have consumed the mass equivalent of millions or billions of stars, might generate particularly large and energetic offspring. Primordial black holes, formed in the extreme conditions of the early universe, might have already produced countless baby universes throughout cosmic history. Each type would contribute uniquely to the cosmic family tree, creating diverse branches of reality, each with their own characteristics derived from their black hole parents. Some would undoubtedly be cosmic dead ends, with physical laws that don't allow for complexity or further black hole formation. Others would be even more fertile than our own, producing abundant black holes and thus abundant cosmic offspring. Over many generations, this process would create what the physicist Lee Smolin calls cosmological natural selection, a gradual evolution of physical laws toward configurations that maximize black hole production. Our universe, with its particular physical constants and laws, might represent not a random selection from infinite possibilities, but the product of many generations of cosmic optimization for black hole abundance. Intriguingly, many of the same conditions that favor plentiful black hole formation also create environments where complexity and potentially consciousness can emerge. Stable stars, necessary for black hole formation through supernovae, also provide the steady energy sources that might nurture living systems. The nuclear reactions that forge heavy elements, eventually forming black holes, also create the chemical diversity needed for complex structures like planets and potentially organisms. This correlation suggests that universes selected for black hole abundance might incidentally create conditions favorable for life and intelligence. We might exist not by cosmic coincidence or design, but as a side effect of selection pressures favoring universes that efficiently create cosmic seeds. For conscious beings contemplating this possibility, black holes transform from objects of fear to sources of wonder, from cosmic dead ends to cosmic nurseries. They remain the most extreme and in some sense destructive forces in our observable universe. But this destruction takes on new meaning when understood as part of a larger creative process that spans universe boundaries. The astronomer and author Carl Sagan famously observed that we are star stuff, our bodies containing elements forged in stellar furnaces. The black hole universe theory extends this profound connection. We are not only star stuff, but potentially universe stuff, our physical substance and informational patterns perhaps destined to contribute to the formation of new cosmic domains through the transformative power of black holes. This expanded cosmic role situates black holes at the center of a universal process that transcends any single cosmos. They become not anomalies or aberrations, but essential participants in an eternal creative cycle, channels through which reality renews itself across universe boundaries. Without them, each universe would be an isolated event, eventually winding down toward heat death with no continuation or renewal. With them, reality becomes an eternal process of cosmic reproduction and variation, an ever-branching tree of universal expressions. This perspective transforms even the eventual fate of our universe from a story of ending to one of transition. In the far future, as stars burn out and galaxies drift apart, black holes will become increasingly dominant features of the cosmic landscape. Eventually, after unimaginable eons, even these black holes will evaporate through Hawking radiation, leaving an apparently empty cosmos. But if the black hole universe theory is correct, This apparent end is merely a transition in the larger story. Each black hole formed during our universe's history would have already seeded the birth of new cosmic domains, carrying forward our universe's legacy into new expressions of reality. Our universe would not truly die, but would live on through its cosmic offspring, each exploring different combinations of physical law and initial conditions. They are no longer the end. They are the womb of the unknown, the points of transition through which reality continues its eternal journey of exploration and expression. Black holes are not where things cease to exist, but where they begin to exist differently, not where patterns are destroyed, but where they are transformed and reborn in new cosmic contexts. This understanding places black holes at the center of a universal story that extends far beyond the boundaries of our observable cosmos. They shape galaxies, consume stars, and now perhaps create worlds, universes with their own space, time, matter, energy, and potentially consciousness. They are not the villains in the cosmic drama, but essential characters in an eternal play of dissolution and recreation, death and birth across the generations of universal existence. The possibility that universes reproduce through black holes introduces a revolutionary perspective on cosmic evolution. Rather than viewing our universe as an isolated event, we can understand it as part of an ongoing process of cosmic reproduction, a self-sustaining system that generates new versions of itself across the generations. This concept of a universe that reproduces itself transforms our understanding of cosmic purpose, evolution, and the apparent fine-tuning of physical laws. The core insight comes from recognizing the potential evolutionary dynamics at play in a multiverse connected through black holes. If each black hole creates a baby universe with slightly modified physical parameters, then over many generations, certain types of universes would become more numerous than others. Specifically, universes particularly good at producing black holes would have more cosmic offspring, eventually dominating the multiverse population. The physicist Lee Smolin has formalized this concept as cosmic natural selection, drawing explicit parallels to biological evolution. Just as species adapt to their environments through the differential reproduction of individuals with beneficial traits, universes might evolve to maximize black hole production, passing down physical laws that enhance reproductive success to their cosmic offspring. This selection process would operate without foresight or intention, through the simple algorithm of variation and selection. Small differences in physical constants between parent and child universes would create variation, while the differential reproduction rates of universes with different black hole abundances would create selection pressure. Over many generations, this process would naturally lead toward universes optimized for black hole production. What makes this framework particularly intriguing is that many of the same conditions that allow for plentiful black hole formation also create environments where complexity and potentially life can emerge. Stable stars, necessary for black hole formation through supernovae, also provide the steady energy sources that might nurture living systems. The nuclear reactions that forge heavy elements, eventually forming black holes, also create the chemical diversity needed for complex structures like planets and potentially organisms. This correlation suggests that cosmic natural selection might inadvertently select for universes capable of generating observers like ourselves. We might exist not through cosmic design or extraordinary coincidence, but as a side effect of selection pressures favoring universes that efficiently create cosmic seeds. This perspective offers a potential solution to the apparent fine-tuning of our universe for the emergence of complexity. The physical constants in our cosmos seem calibrated with remarkable precision to allow for stable stars, diverse chemistry, and ultimately life. Traditional explanations for this tuning include pure chance, an intelligent designer, or the existence of countless random universes, most of which are sterile and lifeless. Cosmic natural selection suggests a different answer. If black holes are the reproductive mechanism for universes, then physical parameters that lead to abundant black hole formation would be favored over many generations. The apparent fine-tuning of our universe would be neither coincidence nor design, but the result of an evolutionary process selecting for universes particularly effective at cosmic reproduction. The specific mechanics of this selection process would depend on how minor variations in physical constants affect black hole production. If slightly stronger gravity leads to more black holes, universes with stronger gravity would become more common over cosmic generations. If a particular ratio between the fundamental forces enhances black hole formation, that ratio would be selected for in the multiverse population. This framework makes a testable prediction. If our universe has been optimized through cosmic natural selection to produce black holes, then small changes to the fundamental constants of nature should generally reduce rather than increase black hole production. Theoretical physicists can model how varying these constants would affect cosmic evolution and black hole abundance, potentially supporting or challenging the cosmic natural selection hypothesis. Initial explorations of this prediction have yielded intriguing results. Many of the same fine tunings that allow for complex chemistry and stable stars also maximize black hole production. For instance, if the strong nuclear force were slightly weaker, stars could not forge heavy elements needed for both complex chemistry and black hole formation. If it were slightly stronger, stars might burn too quickly to allow for either life or abundant black hole creation. These correlations don't prove cosmic natural selection, but suggest the framework deserves serious consideration. They indicate that the same physical parameters that allow for observers like ourselves might have been selected not for our existence specifically, but for their contribution to cosmic reproduction through black holes. The process of cosmic evolution would unfold over unimaginable timescales. Each generation of universes might exist for billions or trillions of years before passing on its cosmic DNA through black holes. Over many such generations, the accumulated selection effects would gradually shape the population of universes toward configurations particularly effective at reproduction. This multi-generational process creates a profound continuity underlying the apparent discontinuities of universe boundaries. While each universe would be causally isolated from its siblings and largely from its parent, the physical laws governing each cosmic domain would reflect its evolutionary heritage, patterns passed down and modified across the generations of universal reproduction. Our universe, with its particular physical constants and laws, would be neither arbitrary nor unique, but one expression of a cosmic evolutionary process that has been unfolding for perhaps uncountable generations. The specific values of fundamental parameters, like the strength of gravity, the mass of elementary particles, or the cosmological constant, would reflect not just our cosmic parentage, but an entire lineage stretching back through ancestors we can never directly observe. This evolutionary perspective transforms how we view cosmic purpose. Rather than being created for a particular end or emerging randomly from nothing, our universe would be part of an ongoing process of exploration and adaptation. The purpose of a universe, in some sense, would be to produce black holes that generate new universes, creating an ever-branching tree of realities. This purpose is not conscious or intentional in the conventional sense, but emerges from the simple mechanism of differential reproduction. Universes better at making black holes have more cosmic offspring, gradually populating the multiverse with realities skilled at both reproduction and the generation of internal complexity. Our existence as conscious observers might be a side effect of this process, but it is not a random accident either. The parallel to biological evolution extends to the concept of fitness landscapes. In biology, species adapt to their environments by moving toward peaks of reproductive fitness in a conceptual landscape of possible adaptations. Similarly, universes might evolve toward peaks in a cosmic fitness landscape, regions of possibility space where physical parameters are particularly conducive to black hole formation. Like biological evolution, cosmic evolution would face constraints and trade-offs. Some changes that might increase black hole production in one respect might decrease it in another. For instance, stronger gravity might create more black holes from stellar collapse, but might also cause galaxies to collapse too quickly, reducing the overall stellar population. The evolutionary process would navigate these trade-offs, finding balanced solutions that maximize total reproductive output. Over many generations, this process would create a diverse multiverse of realities, each with variations in their fundamental parameters, each exploring different possibilities for the laws of physics, for structure formation, for the emergence of complexity. Some branches of the cosmic family tree would be evolutionary dead ends, with physics that doesn't allow for sufficient black hole formation to continue the lineage. Others would be particularly successful, spawning numerous cosmic offspring that carry their physical traits forward with minor modifications. This diversity would not be random, but structured by the evolutionary pressures of cosmic reproduction. The multiverse would contain not all possible universes, but primarily those shaped by selection for black hole abundance. This constraint might explain why our universe has physical laws that allow for both complexity and black hole formation, rather than laws that permit neither or only one of these outcomes. The cosmic reproductive process might even overcome apparent barriers to continued existence. As universes age, they face challenges like the depletion of material for new stars, the expansion of space that isolates galaxies from each other, or the eventual decay of matter itself. But if the black holes formed during a universe's lifetime each create new universes, the cosmic lineage continues even as individual universes reach their endpoints. This continuity across cosmic generations creates a form of immortality for the patterns of existence, even as specific manifestations come and go. The matter and energy that constitute our reality would continue to participate in the cosmic process, flowing through black holes into new expressions, new arrangements, new possibilities in an eternal cycle of transformation. For conscious observers contemplating this possibility, cosmic natural selection offers a framework for understanding our place in a reality larger than any single universe. We are not the purpose of cosmic evolution, but we are one of its most remarkable emergent properties, beings capable of comprehending the very process that led to our existence. The matter that forms our bodies, the carbon, oxygen, and other elements forged in stellar furnaces, exists in forms conducive to complexity because our universe has evolved to produce the stars that create these elements and the black holes that can emerge from stellar death. Our existence is neither accidental nor designed, but emergent from a cosmic process that has been exploring the possibilities of physical law for perhaps uncountable generations. This perspective transforms traditional questions about cosmic origin and purpose. Rather than asking why the universe began or whether it has a purpose imposed from outside, we can explore how universal reproduction shapes the population of cosmic domains over time, creating universes increasingly capable of both continuing the reproductive cycle and generating internal complexity. The apparent fine-tuning of our universe for the emergence of life takes on new significance in this framework. Rather than indicating a cosmic architect designing reality specifically for observers like ourselves, it suggests that parameters conducive to life might be correlated with those that maximize black hole formation and thus cosmic reproduction. We exist not because the universe was designed for us, but because the conditions that allow for black hole formation also allow for complex chemistry, stable energy sources, and potentially consciousness. This correlation between parameters that enable life and those that enable black hole formation remains an active area of research. If cosmic natural selection is correct, we would expect to find that changes to fundamental constants that would make life impossible would generally also reduce black hole production. Preliminary explorations of this prediction have shown intriguing correlations, though the theoretical calculations involved are extremely complex and subject to ongoing refinement. The cosmic evolutionary process would also explain the remarkable stability of physical laws across our observable universe. If our cosmos emerged through a process that selected for particular configurations of physical parameters, we would expect these parameters to be uniform throughout our universe, as they indeed appear to be based on our observations. This uniformity emerges naturally from the reproductive history of our universe, rather than requiring additional explanatory mechanisms. Over vast timescales, the cosmic evolutionary process might lead to interesting possibilities for the far future. If black holes are indeed the reproductive mechanism for universes, and if intelligence can eventually influence black hole formation, might advanced civilizations someday participate in the cosmic reproductive process? Could intelligence eventually shape the parameters of daughter universes by engineering black holes with specific properties? Such cosmological engineering lies far beyond current or foreseeable technological capabilities. Yet if the underlying physical principles are correct, it presents the possibility that cosmic evolution might eventually incorporate not just blind selection, but also elements of directed selection in the far future of universal development. Intelligence emerging within universes might eventually influence the evolution of the multiverse itself, creating a cosmic feedback loop between emergent complexity and the conditions that allow for emergence. This potential interaction between life, intelligence, and cosmic reproduction adds another dimension to the evolutionary picture. Perhaps universes that not only produce many black holes, but also give rise to intelligence capable of creating additional black holes might have an evolutionary advantage over the cosmic timescale. If so, the correlation between conditions favorable for life and conditions favorable for cosmic reproduction might be more than coincidental. The cosmic evolutionary framework also offers a new perspective on the concept of creativity at the largest scales. The multiverse shaped by black hole reproduction would not be static, but dynamically creative, constantly exploring new possibilities through the variation and selection of physical parameters across universe generations. This creativity would not require consciousness or intention, but would emerge from the simple algorithmic process of differential reproduction, just as biological evolution has generated the astonishing diversity and complexity of life on Earth without foresight or planning. This creative process would be constrained, but not completely determined. Random variations in physical parameters between parent and child universes would introduce genuine novelty, allowing the multiverse to explore regions of possibility space that might never have been accessed through a more deterministic process. Yet the selection pressure for black hole abundance would provide direction to this exploration, gradually shaping the population of universes toward configurations that excel at cosmic reproduction. The resulting multiverse would be not a random collection of all possible realities, but an evolved family of related universes, each bearing the imprint of its cosmic lineage, while exploring variations on the central theme of effective reproduction. Like a forest of related but distinct species descending from common ancestors, the multiverse would display both pattern and diversity, both continuity and innovation across its many branches. Not a singular universe, but a growing, living forest of realities. This metaphor captures both the unity and diversity of the cosmic evolutionary picture. Like a forest, the multiverse would consist of many distinct entities sharing common patterns and properties. Like a forest, it would change over time, with new growth emerging as old structures fade. And like a forest, its current state would reflect both its environmental conditions and its evolutionary history, the accumulated effects of variation and selection across countless generations. This vision of cosmic evolution offers a middle path between the extremes of meaningless randomness and predetermined design that often dominate discussions of cosmic purpose. The universe is neither an arbitrary accident nor the product of conscious planning, but the result of a process that generates pattern, complexity, and potentially meaning through the simple mechanism of differential reproduction across universe boundaries. For conscious beings contemplating our place in this larger reality, the cosmic evolutionary framework suggests both humility and wonder. We are not the center or purpose of cosmic evolution, but neither are we accidental byproducts of random processes. We are expressions of a universe shaped by countless generations of cosmic reproduction, exploration, and adaptation, participants in an ongoing creative process that spans realities beyond our direct observation or complete comprehension. Our universe is not alone or unique, but one among many in a vast, growing system of interconnected cosmic domains. Each black hole in our night sky might harbor the seed of another universe with its own stars, galaxies, and perhaps conscious observers, each exploring slightly different expressions of physical law, each contributing to the ongoing creativity of existence. As our cosmic journey draws to a close, we find ourselves returning to where we began, contemplating the profound possibility that black holes, long considered the universe's ultimate endpoints, might actually be cosmic beginnings. We've traversed theoretical landscapes where the death of stars births entire universes, where apparent destruction conceals creation, and where our cosmos might be just one bloom in a vast garden of realities connected through these extraordinary objects. Throughout this exploration, we've seen how black holes challenge our understanding of space, time, and reality itself. At their boundaries, the familiar physics of our universe reaches its limits. Within their depths, new possibilities emerge that transform how we think about cosmic beginnings and endings, about creation and destruction, about the continuity of existence across seemingly absolute boundaries. The mathematics of our best physical theories points toward these possibilities, suggesting that the extreme conditions within black holes might naturally lead to the emergence of new space-time regions, new universes with their own evolutionary paths. What appears as a cosmic dead end from our perspective might be a cosmic genesis when viewed from another angle, a transition rather than a termination. This perspective transforms black holes from objects of fear to sources of wonder. They remain the most extreme environments in our observable universe, places where gravity overwhelms all other forces and where matter is compressed beyond recognition. But this very extremity might be what enables them to serve as bridges between cosmic domains, as wombs of new creation, rather than merely graves for collapsed stars. If this view is correct, then every black hole we observe, from stellar remnants to the supermassive giants at galactic centers, might harbor a universe within. Each one a seed planted in the fertile void, waiting to grow into a reality as vast and complex as our own. The darkness that appears to swallow light forever might actually be channeling it into new expressions beyond our perception, new arrangements of space, time, matter, and energy. This possibility resonates with ancient intuitions about cycles of creation and destruction, death and rebirth that appear in many cultural traditions. Modern physics, through the black hole universe theory, offers a mathematical framework that captures similar insights about the transformative rather than final nature of apparent endings. Nothing truly ends, this framework suggests, but only changes form, continuing its journey in new contexts beyond our direct observation. The theory also offers a potential explanation for the apparent fine-tuning of our universe for complexity. If cosmic evolution operates through the reproduction of universes via black holes, then over many generations, universes particularly good at making black holes would naturally become more common. The physical laws of our cosmos, calibrated with remarkable precision to allow for stable stars, diverse chemistry, and potentially life, might reflect this evolutionary history rather than either extraordinary coincidence or conscious design. For the matter that constitutes our reality, including the atoms that form our bodies, this perspective suggests a kind of immortality. Not personal immortality in the conventional sense, but a continuity of substance and pattern across cosmic generations. The carbon, oxygen, and other elements formed in stellar furnaces might one day contribute to the formation of new stars, planets, and perhaps even life in universes born from the black holes of our cosmos. This cycling of matter and energy, this eternal dance of dissolution and recombination across universe boundaries, creates a profound continuity underlying the apparent discontinuities of black holes. The story of existence is not one of creation and destruction, but of endless transformation. Reality exploring its possibilities through countless iterations, each universe a variation on themes established by its cosmic ancestors. As we gaze at the night sky, we see stars that will one day die, some collapsing to form black holes that might birth new universes. We see galaxies harboring supermassive black holes at their centers, cosmic engines that not only shape the evolution of their galactic domains, but might also generate entirely new realities. We see a cosmos not winding down toward empty silence, but perpetually renewing itself through these extraordinary processes of cosmic reproduction. The darkness between stars takes on new significance in this light. It is not mere emptiness, but pregnant possibility, the backdrop against which the cosmic story unfolds. The black holes that populate this darkness are not holes in the conventional sense, not absences or vacancies, but transitions, thresholds, doorways to other expressions of reality. For conscious observers contemplating these possibilities, black holes invite us to expand our perspective beyond the limits of our observable universe. They remind us that reality might be vaster, stranger, and more interconnected than we can directly perceive, that what appears as an absolute boundary from one side might be a beginning when viewed from another. Even if we can never directly confirm the existence of universes beyond our own, the exploration of these theoretical possibilities enriches our understanding and expands our cosmic perspective. It reminds us that the limits of our knowledge are not fixed but expanding, that questions once considered beyond science might gradually yield to patient investigation and creative inquiry. As you drift towards sleep beneath the canopy of stars, consider the black holes hidden among them, invisible to the naked eye, but revealed by their gravitational influence on surrounding matter. Consider that these cosmic enigmas might be more than ends, might be beginnings of realities we can never directly observe, but can glimpse through the lens of mathematics and theory. Consider that the darkness that appears to consume might actually be creating, that what we perceive as the most destructive force in our universe might be the most creative in the larger tapestry of existence. In the quietest parts of the universe, something stirs, not an end, but a breath, a beginning, perhaps, somewhere beyond the veil of our perception, beyond the event horizons that bound our observable reality. Another sky is being born, another space unfolding, another time beginning its cosmic journey from simplicity toward complexity, from uniformity toward diversity, from potential toward expression. We may never see these other skies, these sibling realities potentially blooming from the black holes in our cosmos, but the possibility of their existence transforms how we understand our own reality, not as an isolated event with an absolute beginning and eventual end, but as one expression in an eternal process of cosmic creativity, one bloom in a garden that transcends the boundaries of any single universe. Sleep now, beneath the stars we know, and dream of the stars we never will. Stars perhaps shining in universes born from the darkness we perceive between our familiar constellations. Dream of the continuous thread of existence flowing through black holes into new expressions, new arrangements, new possibilities in an eternal cycle of cosmic renewal. Creation hidden in collapse, beginning concealed within apparent ending, life emerging from what seems like death. These are not merely poetic metaphors, but potential realities suggested by our best physical theories, glimpses of a cosmic process vaster and more intricate than we can fully comprehend from our position within a single universe. As consciousness fades into the quiet depths of sleep, like light crossing an event horizon, remember that darkness is not the absence of light, but its transformation. That endings are not absolute but transitions. That the black holes punctuating our universe might be not where reality ends, but where it continues in forms and dimensions beyond our direct perception, an eternal process of cosmic exploration and expression that transcends the boundaries of any single universe or any single moment in time. Rest now, as the stars wheel overhead, as galaxies spiral in the darkness, as black holes quietly nurture the seeds of new cosmos within their invisible depths. Rest and be part of this extraordinary process, this endless transformation of matter and energy, pattern and possibility across the generations of universal existence.